Hello there and welcome to Life Beyond Seen, where the world just beneath the surface, whether that is beneath the water beneath the headlines or beneath the easy explanation, tends to hold the most interesting things. There is something about the sea that does this to people. It hides things. It keeps them just out of reach, just past the point where light becomes shadow and shadow becomes nothing. And so when something appears down there, something with shape, something with what looks like geometry, something that seems almost too deliberate to be accidental, the mind reaches for the most human explanation it can find. Someone built this. Someone was here. This was a place. That instinct is not foolish. It is in fact one of the oldest things about us. Tonight we are going to the Ionian Sea, specifically to the waters off the Greek island of Zakynthos, which sits in the northwestern corner of the Aegean world, where the sea runs a particular shade of blue-green in the shallows and deepens into something much older looking as it moves offshore. The Ionian has that quality, a kind of weight to it, even in the bright Greek summer. The light comes through the water in long shifting columns, and the seafloor in the shallows is pale and sandy, and the whole thing feels ancient in a way that is hard to put into words but very easy to feel when you are floating there in a musk and fins, breathing slowly through a snorkel, looking down. In 2013, somewhere near the beach of Alikanas on the northern coast of Zakynthos, snorkelers did exactly that. They were floating in water that was perhaps 2 to 5 meters deep, shallow enough to see everything clearly, shallow enough that the sunlight reached the bottom without much difficulty. And what they saw stopped them. There were columns, or at least things that looked like columns, cylindrical stone shapes, some upright, some tilted, some broken. There were flat surfaces that looked for all the world like paved stone courtyards, the kind you might find in the ruins of an ancient Greek agora or a Roman forum. There were circular formations, ring-shaped structures, some of them several meters across, arranged with what appeared to be a regularity that the natural world does not usually produce. The whole area covered several hundred square meters of seafloor, and it had the unmistakable visual grammar of a place that had once been inhabited, a place that had been built. The snorkelers took photographs. Of course they did, and those photographs began to move. Before we go any further into what happened next, and what was eventually discovered about what those formations actually are, I want to pause for just a moment and ask, where are you listening from tonight? Are you somewhere near water? A coast? A lake? A river? Even just rain on a window? There is something about this particular story that feels right to listen to near water, or at least while imagining it. If you are tucked in somewhere quiet and far from any shore, that is fine too. The sea will come to you through the telling, and if you are enjoying this kind of storytelling, slow, careful, curious, the kind that takes its time with things, it would mean a great deal if you hit the like button and subscribe to Life Beyond Seen. It genuinely helps the channel, and it means more nights like this one, more stories from the edges of what we think we know. Now, back to Zakynthos. The photographs that circulated in the weeks after the initial discovery were striking. Even knowing nothing about archaeology or geology, you could look at them and feel something shift in your chest. The columns were real. The circular formations were real. The flat, paved-looking surfaces were real. None of that was exaggerated or invented. What the snorkelers saw was genuinely there, sitting on the seafloor in perfectly clear Mediterranean water, looking for all the world like the drowned remains of something that had once stood above the waves. And here is the thing that made the whole situation feel so plausible, so immediately reasonable to assume. This part of the world actually has drowned ruins in it. The Mediterranean and the Aegean and the Ionian are not places where underwater archaeology is purely fantasy. They are places where it is an active and productive science, because the coastlines here have been shifting for thousands of years, and settlements that once stood on solid ground are now sitting in several meters of seawater. So when the photographs from Alikanas started spreading, when the words "lost city," and ancient ruins, and, inevitably, Atlantis started appearing in headlines, the reaction was not entirely irrational. The region earns that kind of speculation, at least at first glance. The idea of a drowned settlement off the coast of a Greek island is not inherently absurd. It has happened before, in documented, scientifically verified ways, in waters not far from where these formations were found. That context matters. It is part of why the story moved so quickly and why it lingered. And it is where we need to spend a little time before we get to what the investigators actually found, because understanding why this felt plausible is just as important as understanding why it turned out to be something else entirely. The Ionian Sea has been a crossroads of human civilization for a very long time. Zakynthos itself, which the Venetians called Zante, and which Homer mentions in the Odyssey as a wooded island, has been inhabited since at least the Mycenaean period, roughly 1600 to 1100 BCE. There are known archaeological sites on the island, and the broader region has yielded finds from multiple periods of Greek and pre-Greek history. The ancient town of Zakynthos, which the modern capital sits on top of, has layers going back well over 2,000 years. And the underwater archaeology of the broader Aegean and Ionian region is genuinely remarkable. Off the Laconian coast of southern Greece, there is Pavlopetri, a real Bronze Age settlement, dating to perhaps 3000 BCE, now sitting in 3 to 4 meters of water. It was mapped in detail in 2009, and it has streets, buildings, courtyards, and a cemetery. It is one of the oldest submerged towns ever found. In Egypt, the royal quarter of ancient Alexandria, including what may have been the palace of Cleopatra, lies beneath the waters of the eastern harbour, submerged by earthquakes and subsidence over 2 millennia. In Italy, the Roman resort town of Baiae, once famous for its hot springs and its imperial villas, is now partly underwater in the Bay of Naples, and divers can swim through mosaic floors and past marble statues that have been sitting there since late antiquity. These are not myths. These are mapped, studied, excavated sites. The Mediterranean genuinely swallows its history, and the sea genuinely gives some of it back, in pieces, to those who look carefully enough. The reason this matters for the Zakynthos story is simple. The region has real precedent. The geology of the area, seismically active, subject to significant sea level changes over millennia, sitting on a coastline that has been rising and sinking for thousands of years, means that finding a drowned ancient settlement in these waters would not be surprising. It would be entirely consistent with everything we know about how this part of the world works. The Hellenic subduction zone runs through this region. The African tectonic plate is slowly grinding beneath the Eurasian plate here, and that process drives earthquakes, volcanic activity, and significant shifts in the elevation of the seafloor and the coastline. Zakynthos sits almost directly above this zone, and the island has a long history of seismic events, the most famous being the catastrophic earthquake of August 1953, which measured 7.2 in magnitude and essentially levelled the island's capital, destroying most of its Venetian-era architecture. If a single earthquake in living memory could do that to a city on solid ground, it is not difficult to imagine what centuries of seismic activity might do to a coastal settlement, how it might tilt it, crack it, submerge it, and leave it sitting in shallow water looking exactly like a ruin. So the snorkelers at Lecanus were not being credulous or naive. They were looking at something that genuinely resembled ruins, in a region where ruins genuinely exist underwater, on an island with a documented ancient history, in a sea that has been reshaping coastlines for as long as humans have been living on them. Their instinct, that this was something built, something human, something lost, was a perfectly reasonable first response to what they were seeing. And what were they seeing exactly? Let us be specific because the details matter. The formations at Alicana sit at depths between roughly 2 and 5 meters, which is very shallow, shallow enough to snorkel comfortably, shallow enough that the visibility is excellent in clear weather, shallow enough that the shapes are immediately legible from above. The most striking features are the large donut-shaped rings, circular or near-circular formations of stone, some of them several meters in diameter, that sit flat on the seafloor and look from above like the foundations of round structures or the bases of pillars. There are also cylindrical columns, or column-like shapes, some standing more or less upright, some fallen and broken, that look almost exactly like the columns you would find in the ruins of a Greek temple or a Roman bath. The surfaces between these features are flat and relatively even, with a texture that reads, visually, as paving, as worked stone laid deliberately to create a floor. The overall effect, especially in photographs taken from above in good light, is of a complex, a place, something that was designed. It is worth sitting with that image for a moment, because the visual impression is genuinely convincing. This is not a case of people squinting at a vague lump of rock and deciding it looks like something. The shapes are distinct. The geometry is real. The regularity is there. Whatever these formations are, they are not random rubble. They have a form that the eye recognizes and the brain immediately begins to interpret. Which is precisely where things get interesting. Because when Greek authorities were notified, when the Ministry of Culture and the Ephorate of Underwater Antiquities sent investigators to look at the site properly, what they found, and more importantly what they did not find, began to tell a very different story than the one the photographs seemed to be telling. The question that was now sitting at the centre of everything was deceptively simple. What exactly had those snorkelers found? The formations were real. The shapes were real. The seafloor off Alicarnus genuinely looked, in certain lights and from certain angles, like the floor plan of a drowned city. But looking like something and being that thing are two very different propositions, and the Ionian Sea, it turned out, had its own answer ready. One that had nothing to do with ancient Greeks or Roman engineers or any human hand at all. What that answer was, and how scientists eventually pieced it together, is a story that moves through geology and chemistry, and the slow, patient work of people who examine rocks under microscopes and measure isotope ratios in mineral samples. It is, in its own way, just as remarkable as any lost city would have been, maybe more so. Because the process that built those formations in the shallow water off Zakynthos is older than human civilization by a margin that is almost impossible to hold in the mind, and it worked without any blueprint, without any architect, without any intention at all, and it produced something that fooled the human eye completely. To understand why the Zakynthos discovery felt so believable, and why it attracted the attention it did almost immediately, it helps to spend a little time with the island itself, and with the broader world it sits inside. Because Zakynthos is not a blank place. It is not a remote, archaeologically empty island that had never produced anything of historical interest before a few snorkelers stumbled across some unusual shapes on the seafloor. The island has weight to it. It has layers, and those layers matter when you're trying to understand why the initial assumption of a lost city was not just understandable, but genuinely reasonable. Zakynthos is the southernmost of the main Ionian islands, sitting in the sea that separates Greece from Italy, roughly 20 kilometres off the western coast of the Peloponnese. It covers about 405 square kilometres, which makes it a medium-sized Greek island, not enormous, but substantial enough to have supported continuous human habitation across a very long stretch of time. The island's name appears in Homer. In the Odyssey, Zakynthos is mentioned as a place that sent suitors to court Penelope during Odysseus's long absence, which places it, at least in the mythological geography of the ancient Greeks, as a settled and significant location. Whether that reflects genuine Bronze Age memory or is simply poetic convention is a question scholars debate, but the point is that Zakynthos has been known and inhabited for a very long time. The physical record supports this. Mycenaean-era finds have been documented on the island, suggesting occupation during the late Bronze Age, roughly 1600 to 1100 BCE. The ancient town of Zakynthos, which sat roughly where the modern capital now stands, was an established settlement in the classical period, and the island was prosperous enough to mint its own coins. During the Hellenistic and Roman periods, it continued to be inhabited and economically active. Later came Byzantine control, then Frankish, then Venetian, and it was under Venetian rule, which lasted from 1484 until 1797, that the island developed much of the urban character that defined it before the 1953 earthquake. That earthquake, as mentioned before, was devastating, but the layers beneath the rubble go back much further. The island is, in the proper sense of the word, an archaeological landscape. It has been studied, surveyed and dug. It gives up finds. So when something unusual appeared in the shallow water off the northern coast, near the beach at Ali Khanaz, the instinct to frame it as an archaeological discovery was not coming from nowhere. It was coming from a place that had earned that instinct. The Ionian Sea around Zakynthos is not some unexplored frontier. It is a body of water that has been sailed, fished and lived beside for millennia, and its floor, in the shallower zones at least, has been looked at by divers, fishermen and researchers for decades. Finding something new there was not impossible. Finding something significant was not impossible. The question was always going to be what kind of significance the discovery actually had. And here is where the broader Mediterranean context becomes important, because the Zakynthos find did not exist in isolation. It appeared against a backdrop of genuine, well-documented underwater archaeological sites in the same general region, sites that made the idea of a drowned ancient settlement in these waters not just plausible, but almost expected. The Mediterranean is, in a real sense, an archaeological sea. Its floor contains the physical remains of thousands of years of coastal civilization, because the relationship between land and sea in this region has never been stable. Sea levels have risen and fallen, coastlines have subsided and emerged, earthquakes have tilted entire coastal zones into the water. The result is that a significant number of ancient sites that were once on dry land are now partially or entirely submerged. The most famous example in the eastern Mediterranean is probably Alexandria's submerged royal quarter off the coast of Egypt. The ancient harbour district of Alexandria, including what is believed to be the site of Cleopatra's palace complex, began sinking into the sea sometime in the early centuries of the Common Era, likely due to a combination of earthquakes, tsunamis, and the gradual subsidence of the Nile Delta. French archaeologist Frank Godiot led systematic underwater excavations there beginning in the 1990s, and the results were remarkable. Statues, columns, sphinxes, the foundations of large buildings, all sitting in the shallow water of Abukir Bay. This is real. It is mapped. It is ongoing. Closer to Zakynthos, off the southern coast of the Peloponnese, there is Pavlopetri, possibly the oldest known submerged town in the world. It was first noticed by oceanographer Nicholas Fleming in 1967, and a survey was conducted in 1968. But it was only in 2009 that a detailed mapping project by the University of Nottingham revealed just how extensive the site was. Pavlopetri dates to the Bronze Age, with occupation going back at least to around 2800 BCE. It sits at a depth of 3 to 4 metres, which is almost exactly the same depth range as the Zakynthos formations. The site includes clearly defined streets, buildings, courtyards, and what appear to be chamber tombs. It covers around 30,000 square metres. It is by any measure a genuine drowned city, and it sits less than 200 kilometres from Zakynthos. That is not a distant comparison. That is practically a neighbour. Then there is Baiae, in the Bay of Naples, already mentioned in the previous part of this narration, where Roman-era structures, mosaic floors, and statuary have been sitting underwater since late antiquity, accessible to divers, and now the subject of an active archaeological park. And there are smaller sites scattered throughout the Aegean and Ionian regions, submerged harbours, drowned field systems, coastal settlements that slipped below the waterline during the long process of sea level rise that followed the last ice age, when global sea levels rose by roughly 120 metres over the course of several thousand years. Much of what was coastal land 10,000 years ago is now seafloor, and in the Mediterranean, where ancient people lived densely along coastlines, that means a great deal of the archaeological record is literally underwater. This is the context in which the Zakynthos discovery landed in 2013, not a context of skepticism, but a context of genuine precedent. The region produces real underwater ruins. The geology explains why they exist. The depth range, 2 to 5 meters, is exactly where you would expect to find sites that were coastal or near coastal in antiquity and have since been inundated. The visual appearance of the formations, with their columnar shapes and flat surfaces, fit well enough with what Greco-Roman architectural remains actually look like on the seafloor, and the island itself has a documented ancient history that made the idea of a drowned settlement adjacent to it entirely consistent with what was already known. It is worth being clear about this because it is easy in retrospect, knowing what the scientific investigation eventually found, to treat the initial excitement as naive or credulous. It was not. The people who looked at those photographs and thought they were looking at a lost city were not being foolish. They were applying a reasonable interpretive framework to something that genuinely fit that framework. The error, if you want to call it that, was not in the instinct but in the speed. The photographs circulated before the investigation happened. The headlines appeared before the analysis was done. That is a pattern that comes up again and again with discoveries of this kind, and it is worth understanding rather than simply criticising, because it tells you something about how human beings process the idea of the past and about how media moves in relation to science. Greek authorities did respond. The Ministry of Culture was notified, and the Ephorate of Underwater Antiquities, the branch of the Greek government responsible for protecting and investigating underwater heritage, sent investigators to the site. This was not a casual look. The Ephorate takes its work seriously. Greece has some of the most extensive underwater cultural heritage in the world, and the institutions responsible for managing it are experienced and methodologically careful. The investigators who went to Zakynthos knew what ancient underwater sites look like. They knew what to look for, and they knew what would be missing if the site were not what it appeared to be. What they found and what they did not find would gradually shift the conversation from archaeology to geology. But that shift was not immediate, and it was not simple. The formations were genuinely unusual. The shapes were striking enough that even experienced investigators paused. The visual case for human construction was, in purely optical terms, a strong one. The donut rings, the cylindrical columns, the flat paved-looking surfaces, these were not ambiguous blobs. They were specific, repeating geometric forms, and geometry in nature tends to attract the human eye for good reason, because in most human experience, regular geometry is a sign of intention. But intention is exactly what the investigation began to question. And the questions it raised were not about the visual appearance of the formations. They were about everything else, about what was present and what was absent, about the material the formations were made of and how that material behaved under analysis, about what the seafloor around the structures contained, or rather, what it did not contain. Because the absence of certain things in archaeology can be just as telling as the presence of others, sometimes more so. The region around Zakynthos, as has been established, has a real ancient history. If the formations at Zakynthos were the remains of a human settlement, even a modest one, even a working harbour or a small coastal community, there should be traces. Not necessarily spectacular traces, not necessarily inscriptions or statuary, but something. The ordinary debris of human life accumulates everywhere people live and work, and it persists in underwater environments remarkably well. Pottery in particular is almost indestructible. Sherds of ancient ceramics survive for thousands of years on the seafloor. At Pavlopetri, at Baiae, at Alexandria's submerged district, the pottery is everywhere, mixed into the sediment, sitting in corners, scattered across floors. It is one of the most reliable indicators of human occupation, and its absence is significant. At Zakynthos, the investigators found none. No pottery, no coins, no metal objects, No organic remains, no tool marks on the stone surfaces, no evidence of quarrying, the characteristic marks left when stone is cut and shaped for building. No construction joints of the kind you see when blocks are fitted together. No variation in the type of stone used, which is unusual for human construction, where different materials are typically selected for different structural purposes. The formations were composed entirely of a single mineral type, consistently throughout the entire site, and that consistency, paradoxically, was one of the first strong clues that what was sitting on the seafloor off Alicanas had not been put there by human hands. The mineral in question is dolomite, and the story of how dolomite forms in this kind of environment, and why it forms in shapes that look so remarkably like columns and paving stones, is the geological heart of the Zakynthos mystery. It is a story that takes place over millions of years, in darkness, through chemistry rather than craft, and it produces results that the human eye, trained by thousands of years of living among built things, reads immediately as architecture. The investigators who examined the site carefully, and the researchers who later published their findings in 2016, would eventually lay out exactly how this happened, and why. But to understand their explanation, it helps to first understand what dolomite is, how it forms, and why the particular conditions beneath the seafloor of the Ionian Sea are exactly the kind of conditions that produce it in such strikingly organised shapes. That explanation, when it came, would not diminish the site. If anything, it would make it stranger and more interesting than a drowned city would have been. Because a drowned city is something humans understand. It is something humans built, and then lost, and then found again. What the formations at Alicanas actually represent is something the planet built entirely on its own, following rules that have nothing to do with human intention, and everything to do with the slow, pressurized chemistry of rock and fluid and time, and the fact that those rules produce something so visually convincing, so apparently deliberate, so genuinely architectural in appearance. That is the part of this story that deserves to be looked at carefully. So, let us go back to the beginning of this particular story. Not the geological beginning, that comes later, but the human beginning. The moment when someone floating in the clear, warm water off the northern coast of Zakynthos looked down and saw something that stopped them. It was 2013. The beach at Alicanas sits on the northern part of the island, quieter than the busier resort areas to the south. The kind of place where the water is shallow and calm and the seafloor is visible from the surface on a good day. The Ionian Sea in that region has a particular clarity to it, especially in the shallower zones near the coast, where the light comes through in long shifting columns and the bottom is close enough to read. Snorkelers in that area are not unusual. People float out from the shore regularly, masks on, watching the sand and rock below. It is an ordinary thing to do on a Greek island in the summer. What was not ordinary was what some of those snorkelers began to notice on the seafloor. At a depth of roughly 2 to 5 meters, shallow enough to see clearly, shallow enough in places to almost touch the bottom without diving, there were formations, stone formations, large ones, and they did not look like scattered rocks or irregular reef structures. They looked, quite specifically, like the remains of something that had been built. The shapes that drew attention first were the circular ones, large rings of stone, roughly donut-shaped, sitting on the seafloor with a kind of deliberate regularity that was hard to dismiss. Some of them were a metre or more across. They were not isolated. There were multiple rings, distributed across an area that covered several hundred square metres. Between and around them were other features, flat surfaces that looked like paving, smooth and horizontal in a way that natural rock rarely manages. And there were cylindrical protrusions, column-like forms rising from the seafloor, some of them intact, some broken and lying on their sides in the way that columns in actual ruins tend to fall. The whole arrangement, seen from above through a mask and a metre or two of clear water, looked extraordinarily like the ground plan of a building, or several buildings, the kind of thing you might see in a photograph of an excavated Greek site. The low stone outlines of walls and floors, the stumps of columns, the circular bases of structures long since collapsed. The people who saw this took photographs. Of course they did. This was 2013 and waterproof cameras and phones were already common enough that documentation was instinctive. The images they captured were clear and detailed enough to show what they were seeing, and the visual case those images made was, by any honest assessment, a compelling one. Looking at the photographs without any prior knowledge, the reasonable conclusion was that this was the remains of a human settlement. The geometry was too specific, too repeating, too organised looking to read any other way. Those photographs moved quickly. Within a short time they were online, and once they were online the response was immediate and loud. Greek media picked up the story first, which made sense. This was a discovery in Greek waters, potentially of Greek historical significance, and the Greek press has always paid close attention to archaeological finds for good reason. The country's relationship with its ancient past is deep and genuine, and a potential underwater ruin off one of the Ionian Islands was exactly the kind of story that resonated. But the story did not stay local for long. International outlets followed. The photographs were striking enough to carry the story across language barriers without much translation needed. You could look at the images and understand immediately why people were excited. The language that appeared in the coverage was, in retrospect, predictable. Lost City was used early and often. Ancient Greek ruins appeared in headlines. Some outlets went further, and the word Atlantis surfaced, as it almost always does when an underwater stone formation is discovered anywhere in the Mediterranean or the Atlantic. Plato's imagined sunken civilization has been attached to so many actual sites over the centuries that its appearance in this context was almost automatic, a reflex more than a considered claim. But it landed, as it always does, because the idea of Atlantis taps into something that does not require historical accuracy to feel meaningful. The romance of a civilization swallowed by the sea is old and powerful, and the photographs from Alicana fed it naturally. Tourism interest in the area around Alicana spiked noticeably. People wanted to see it. The formations were in shallow water, accessible to anyone with a mask and basic swimming ability, which meant this was not a discovery that required a research vessel or a diving certificate to appreciate. You could, in theory, swim out from the beach and float above what looked like a lost city on a Tuesday afternoon. That accessibility was part of what made the story spread so fast and stick so effectively. It was not abstract, it was visitable. And Zakynthos, already a popular tourist destination, found itself with a new point of interest that had appeared without anyone planning for it. Meanwhile, the formal response was being organised. The Ministry of Culture in Greece was notified, and the Ephorate of Underwater Antiquities began preparing to send investigators. This is the body within the Greek state responsible for underwater cultural heritage, for locating, documenting, protecting, and investigating submerged sites of potential historical significance. Greece has more underwater cultural heritage than almost any other country in the world, and the Ephorate is experienced in working with it. Its investigators have seen genuine Bronze Age harbours, Hellenistic shipwrecks, Roman cargo vessels, ancient anchors, amphory fields. They know what an underwater archaeological site looks like in detail, not just in general impression. The decision to investigate was the right one, and it was taken seriously. The formations were not dismissed because they were in shallow water, or because the initial reports came from recreational snorkelers rather than professional divers. If anything, the visual evidence in the photographs warranted a careful look precisely because it was so visually specific. The Ephorate sent people who knew what they were doing and knew what questions to ask. What the investigators encountered when they reached the site was, in visual terms, exactly what the photographs had suggested. The formations were real, they were substantial. The donut-shaped rings were there, sitting on the seafloor in their repeating arrangement. The flat surfaces were there. The cylindrical column-like forms were there, some upright, some toppled. The scale of the site was genuine. Several hundred square metres of these formations spread across the seafloor at that comfortable, visible depth of 2 to 5 meters. In the clear water, with Mediterranean light filtering down from above, the site had a quality that was hard to describe as anything other than architectural. Even experienced investigators, people who had spent careers working with actual underwater ruins, found the visual impression striking. But visual impression is where archaeology starts, not where it ends. The investigators began to look more carefully and more specifically at the things that should be present at human habitation site and were not. The first and perhaps most significant absence was pottery. In underwater archaeology, ceramic fragments are among the most reliable indicators of human activity. Pottery is virtually indestructible over archaeological timescales. Sherds survive in sediment for thousands of years without significant degradation. At any site where people lived, worked, traded, cooked or stored goods, pottery accumulates. It breaks, it gets discarded, it falls into corners and gets buried in floors and washes into nearby sediment. At genuine underwater ancient sites, Pavlopetri, Baiae, the submerged harbour at Caesarea Maritima, pottery is everywhere. You find it in the sediment matrix lying on surfaces, embedded in the structure of the ruins themselves. It is one of the things that tells you, unambiguously, that people were here. At Alicanas, the investigators found no pottery. None. Not a single sherd. Not a fragment. The sediment around the formations and between them contained no ceramic material at all. There were no coins, no metal objects of any kind, no organic remains, no wood, no bone, no plant material of the type that sometimes survives in anaerobic underwater sediment, no inscriptions on any of the surfaces, no tool marks, the characteristic traces left when stone is cut, shaped, dressed or fitted, the marks of chisels and saws and the particular wear patterns that quarried stone shows. No construction joints, the deliberate fitting surfaces where one block is laid against another with careful attention to contact and load. And crucially, no variation in the type of stone across the site. Human construction uses different materials for different purposes. Harder stone for structural elements, softer stone for infill, different quarry sources for different phases of building. The formations at Alicanas were composed throughout of a single consistent mineral type. Every column, every ring, every flat surface, the same material, the same composition, the same consistent character. That last point, the uniformity of material, was one of the things that began to shift the investigators' thinking most clearly. In a human-built structure, even a simple one, you expect variation. Different builders at different times using different sources, repairs made with available material, modifications that introduce new stone. The uniformity at Alicanas was not what a settlement looks like. It was what a single geological process looks like. The mineral throughout the site was dolomite, not ordinary limestone, which is the most common building stone in the ancient Mediterranean world, and which you would expect to find at a Greek archaeological site. Dolomite, a specific carbonate mineral with a specific chemistry and, more importantly, a specific set of conditions under which it forms. And those conditions, as the investigators and the researchers who followed them would eventually explain, are not the conditions of a quarry or a building site. They are the conditions of a seafloor or a shallow marine environment, where particular fluids are moving through particular kinds of rock over very long periods of time. The formations at Alicanas were not built, they grew. Not in the way that coral grows, or in the way that crystals grow in a laboratory, but in the slow, pressurized, chemically driven way that minerals precipitate out of solution when the right fluids meet the right conditions in the right place. The shapes that resulted from that process, the rings, the columns, the flat surfaces, were not the product of human intention. They were the product of fluid dynamics and mineral chemistry, playing out over a timescale that makes human civilization look very brief indeed. Understanding exactly how that process works, how a chemical reaction happening in darkness beneath the seafloor can produce shapes that look so specifically architectural requires a closer look at the geology of the site and the particular mechanism that researchers identified as responsible. The 2016 study, published in Marine and Petroleum Geology, would lay this out in careful detail, but the investigation that preceded that publication, the methodical, experienced artifact hunting investigation by the Ephorate of Underwater Antiquities, had already established the essential negative case. This was not a human site. The question that remained was what it actually was, and how the planet had managed to produce something so visually convincing without any human involvement at all. That question leads directly into the geology of the Ionian seafloor, into the behaviour of hydrocarbons migrating upward through fractured rock, and into the specific chemistry of dolomite formation in shallow marine environments. It leads, in other words, to an explanation that is, in its own way, considerably stranger and more remarkable than a lost city would have been. So let us slow down for a moment and sit with what the investigators actually had in front of them, because this part of the story is easy to rush past, and it deserves some patience. The Ephorate of Underwater Antiquities is not a casual organisation. It is the branch of the Greek Ministry of Culture specifically responsible for the documentation, protection, and study of Greece's submerged cultural heritage, and Greece has a great deal of it. The people who work in that field have spent careers examining genuine underwater ruins, Mycenaean harbour installations, Byzantine shipwrecks, submerged Bronze Age settlements, Roman-era port infrastructure. They know what an ancient site looks like, and more to the point, they know what it feels like to be at one. There is a particular kind of sediment disturbance around human-built structures, a particular way that artefacts accumulate, a particular relationship between the shapes of stones and the logic of construction. When the investigators arrived at Alicarnus and began their systematic examination of the formations, they were not guessing. They were applying a very specific professional framework to what they found, and what they found, or rather what they did not find, is where the story turns. The absence of pottery has already been mentioned, but it is worth dwelling on for a moment longer, because for underwater archaeologists it is not just one data point among many. It is close to definitive on its own. Pottery in the ancient Mediterranean world was everywhere. It was the plastic of antiquity in a sense, cheap to produce, endlessly useful, made in enormous quantities, and essentially indestructible once fired. A cooking pot breaks and becomes 100 sherds that sit in the ground for 3,000 years without dissolving. Storage jars, wine amphorae, oil containers, drinking cups, lamps, all of them made of fired clay, all of them leaving fragments behind when they break. At Pavlopetri, the Bronze Age underwater city off the Laconian coast that was mapped in detail starting in 2009, pottery has been recovered from across the entire site. It lies in the sediment, it sits on the ancient floors, it tells researchers which periods the site was occupied and what people were doing there. At the submerged portions of Baiae in the Bay of Naples, pottery is one of the primary tools researchers use to date different phases of the site. Even at poorly preserved sites, even at sites that have been heavily disturbed by currents or biological activity, you find pottery. The sediment holds it. The weight of it keeps it in place. There is no realistic scenario in which a genuine ancient habitation site of several hundred square metres, sitting in only 2 to 5 metres of water, would contain no ceramic material whatsoever. The absence is not a gap in the evidence. It is itself a piece of evidence, and a fairly loud one. The same logic applies to the other absences. Coins are another near-universal marker of ancient sites in the Greek and Roman world. Metal corrodes, but it does not disappear. Bronze and silver coins survive in underwater sediment for millennia, often with their surfaces degraded but their shapes intact. At Alicarnus, none. Metal objects of any kind, tools, fasteners, decorative elements, The simple iron or bronze hardware of everyday ancient life? None. Organic materials are trickier because they depend heavily on local sediment conditions for preservation, but in anaerobic low-oxygen sediments of the kind found at some underwater sites, wood and bone and plant matter can survive for thousands of years. At Alicanas, the sediment conditions were not particularly favourable for organic preservation, so the absence of organics is less significant on its own. But it fits the pattern. The tool marks deserve particular attention because they are one of the most physically specific things investigators look for. When a stone is quarried, it shows it. Ancient quarrying techniques, iron chisels, abrasive saws, the use of wooden wedges driven into natural fractures, leave characteristic marks on stone surfaces. The cut faces of quarried blocks have a texture that is distinct from naturally broken or naturally weathered stone. When blocks are dressed, shaped to fit together, the contact surfaces show wear patterns that are specific to that process. When stone is transported, it sometimes shows damage from handling, from ropes, from the friction of being moved across other surfaces, and when stone is laid in construction, the mortar joints, or in dry stone construction, the carefully fitted contact surfaces leave traces that are identifiable under examination. None of these traces were present at Alicanas. The surfaces of the dolomite formations were smooth in places and roughened in others, but the texture was consistent with natural weathering, natural erosion, and natural crystal growth, not with any of the mechanical processes involved in quarrying, shaping, or constructing with stone. The absence of construction joints is related to this, but slightly different. In any built structure, even a simple one, individual stones are placed in deliberate relationship to each other. They are stacked, fitted, bonded with mortar, or carefully shaped to interlock. This means that at the junction between one stone and another, you can see the interface, the point where one element ends and another begins, the deliberate decision about how to join them. At Alicanas, there were no such joints. The formations did not consist of individual assembled pieces. They were continuous. The column-like shapes were not stacked drums of stone as Greek columns typically are, assembled from separate cylindrical sections. They were single continuous masses of dolomite, with no internal divisions, no assembly lines, no evidence of being put together from parts. This is a very specific and important observation, because it points directly toward a formation process in which the material grew as a single body rather than being assembled from multiple components. And then there is the uniformity of material, which the investigators found throughout the site. This point is subtle enough that it is worth explaining carefully, because it is not immediately obvious why it matters. When ancient builders constructed something, a temple, a harbour wall, a house, a public space, they used whatever stone was locally available and appropriate for the purpose. In Greece, this usually meant limestone of various types, sometimes marble for important buildings, sometimes harder volcanic stone for particular structural needs. Even within a single construction project, you often see variation, different quarry sources used at different times, repairs made with slightly different stone, foundations of one material and walls of another. Over the lifetime of the settlement, the variation increases. Different periods of construction leave different material signatures. At Pavlopetri, researchers can distinguish different phases of the site, partly through the materials and construction techniques used in different areas. At Baiae, the Roman concrete and the earlier Greek stonework are distinguishable. Human construction, in other words, is materially heterogeneous. It reflects the decisions and resources of many people over many years. The formations at Alicanas showed none of this heterogeneity. From one end of the site to the other, across all the different shapes, the rings, the columns, the flat surfaces, the material was the same. Dolomite. Consistent in composition, consistent in texture, consistent in the way it had formed. There was no variation that would suggest different phases of construction, different builders, different purposes for different parts of the site. The uniformity was total. And total uniformity across a site of several hundred square meters is not what human construction looks like. It is what a single geological process looks like. A process that operated across the entire area at the same time, under the same conditions, producing the same material throughout. This was the point at which the investigators and the researchers who would later analyse the sites more formally began to articulate what they were actually looking at. Not a lost city, not a submerged settlement, not evidence of any human activity at any period. What they were looking at was a geological formation, specifically a formation produced by the precipitation of dolomite from fluids moving through the seafloor. The shapes that had looked so architectural, so deliberately arranged, so unmistakably human in their geometry, were the product of a natural process that had nothing to do with human intention and everything to do with the chemistry of carbonate minerals and the behaviour of fluids under pressure. It is worth pausing on the specific visual features that had been so convincing, because understanding why they look the way they do is part of understanding the explanation that followed. The most striking elements, the ones that appeared in all the photographs and drove the media coverage, were the cylindrical column-like forms. They really do look like columns. They are roughly circular in cross-section. Some of them are upright. Some have fallen, which adds to the ruin aesthetic. A standing column is impressive, but a fallen column is somehow even more evocative of a lost civilization, because it implies something that once stood and has since collapsed. The columns at Zakynthos are not perfectly uniform in size, but they are consistent enough in their general form to read, visually, as a type. And the human brain, encountering a set of cylindrical vertical forms of roughly similar dimensions, reaches immediately for the most familiar explanation. These are columns, and columns mean a building, and a building means people. The concentric ring formations are similarly compelling. They sit flat on the seafloor, or close to flat with a raised outer rim and a central depression, and they look, genuinely strikingly look, like the foundations of circular structures, or like the bases of large storage vessels, or like the remains of wells or cisterns. The largest of them are several meters across. In the clear, shallow water, with the light coming down from above and casting shadows into the depressions, they have a quality that reads as deliberate. The flat, paved-looking surfaces between and around the formations complete the picture. Your eye connects the columns, the rings, and the flat areas and constructs a space, a courtyard, a public area, a harbour installation. The visual logic is almost irresistible, but the investigation had now established carefully and methodically that the visual logic was wrong. The formations were not what they looked like. The question that remained, the question that the 2016 study in marine and petroleum geology would take up in detail, was what they actually were and how precisely the natural process responsible had managed to produce shapes so specifically evocative of human construction. That question required a different kind of expertise than archaeology. It required geology, and specifically the geology of carbonate mineral formation in marine environments. It required an understanding of what happens when certain kinds of fluids move upward through the sea floor, and what kinds of shapes those fluids produce as they go. It required, in other words, a shift from the question of what people built here to the question of what the Earth built here, and why it built it in these particular shapes, in this particular place, over a timescale that has very little to do with human history, and everything to do with the deep history of the planet itself. The researchers who took up that question, a team from the University of Athens, working with material samples from the site and the methods of modern geological analysis, found an explanation that was, in several respects, more interesting than a lost city. Not more emotionally satisfying, perhaps, not more immediately exciting to a headline writer or a casual visitor floating above the formations in a snorkel mask, but more interesting in the way that genuinely strange natural processes are interesting, because the mechanism is specific, because it operates on a scale that is hard to fully picture, and because it produces results that the planet has been producing, quietly and without any audience, for millions of years. That mechanism begins with methane, or more precisely, it begins with the movement of hydrocarbon-rich fluids upward through fractured seafloor rock, driven by the particular tectonic conditions of the Ionian Sea. Conditions that are, as it happens, among the most geologically dramatic in all of Europe. Understanding the explanation for the Zakynthos formations means understanding something about the sea floor beneath them, and the forces that have been shaping it for far longer than any civilization has existed to observe it. The 2016 study, published in the journal Marine and Petroleum Geology, was led by a team of University of Athens researchers that included Professor Ioannis Iliopoulos and colleagues working across geology, geochemistry, and sedimentology. Their paper was not written for a general audience. It was a technical document, dense with petrographic data and isotope ratios and mineral classification terminology. But the core finding, once you pull it out of the scientific language, is something that can be explained clearly, and it is worth explaining carefully, because the mechanism is genuinely unusual, and the shapes it produces are not accidental. The formations are composed of dolomite. That much had already been established during the initial investigation, but the 2016 study went further, asking not just what the material was, but how it had formed, and what that formation process implied about the origin of the shapes. Dolomite is a carbonate mineral, magnesium-calcium carbonate if you want the chemistry, and it is harder and denser than regular limestone. It forms through a process called diagenesis, which is a broad term for the physical and chemical changes that happen to sediment after it has been deposited but before it has been fully converted to rock. One specific diagenetic pathway produces dolomite through the interaction of mineral-rich fluids with existing carbonate sediment, replacing calcium atoms with magnesium atoms in the crystal lattice over time. But the dolomite at Zakynthos formed through a somewhat different and more specific route, one that is tied directly to the behaviour of fluids rising from below. The key process is called orthogenic carbonate formation. Orthogenic means formed in place. The mineral crystallised exactly where it now sits, rather than being transported there from somewhere else. What drives this formation is the upward migration of hydrocarbon-rich fluids, including methane, through cracks and pores in the seafloor sediment. When these fluids encounter the chemistry of the overlying seawater and the microbial communities that live within the sediment, a reaction occurs. The fluids are oxidized, partly through microbial activity, and this oxidation raises the alkalinity of the surrounding pore water. When alkalinity rises sharply in a carbonate-saturated environment, minerals begin to precipitate. They crystallize out of solution and harden into solid rock. The result is a process sometimes called concretion, a hard mineral mass forming within softer surrounding sediment, growing outward from the point where the fluid is most concentrated. It sounds almost mundane when described that way. Fluid rises, chemistry changes, minerals crystallize. But the results of this process, played out over thousands or millions of years in the right geological setting, are anything but mundane. They are, in fact, exactly what you see at the seafloor near Alicanus. The reason the shapes form the way they do comes down to the geometry of how the fluids move. Methane and other hydrocarbons do not rise uniformly through the seafloor. They travel along pathways, fractures, fault lines, permeable channels through otherwise impermeable rock. These pathways have geometry, they have direction and shape, and the carbonate minerals that precipitate around them inherit that geometry, because the precipitation happens most intensely wherever the fluid concentration is highest, which is at and immediately around the conduit through which the fluid is travelling. When a hydrocarbon-rich fluid rises through a single narrow vertical conduit, a crack or a pipe in the sediment, the precipitation occurs in a cylinder around that conduit. The fluid is most concentrated at the centre, and the mineral crystallization radiates outward from it, producing a roughly circular cross-section. The result, once the surrounding softer sediment erodes away, is a cylindrical structure, a column. Not a carved column, not a placed column, not a column that anyone shaped with a chisel or moved into position. A column that grew, atom by atom, around the path that a fluid took through rock. The resemblance to an architectural column is not coincidental in the sense of being random. It is the natural consequence of fluid moving through a cylindrical channel and precipitating minerals as it goes. But it has nothing to do with human intent. The concentric ring formations follow a related logic. When fluids spread outward from a central point, when they reach a layer of sediment where they can move laterally rather than continuing to rise vertically, they radiate outward in all directions from that point. The precipitation follows the fluid, forming a disc or ring shape, thickest at the centre where the fluid first arrives and thinning toward the edges. The raised outer rim of some of the formations reflects the way the precipitation front moves through the sediment. The central depression reflects the original conduit point. Seen from above, in the clear shallow water of Alicanus Bay, these formations look exactly like the foundations of circular structures or like the stone rings of ancient wells. They are neither. They are the record of a fluid spreading through sediment, written in dolomite. The flat, paved-looking surfaces are produced by a third variant of the same basic mechanism. When fluids spread laterally through a horizontal sediment layer, a permeable band sandwiched between less permeable layers above and below, the precipitation hardens that entire layer uniformly. The result is a flat, dense sheet of carbonate rock, extending across whatever area the fluid reached. Over time, the softer sediment above and below this sheet erodes. The hard sheet remains, exposed on the seafloor, looking for all the world like a paved surface, like a courtyard floor, like the kind of thing a harbour builder or a city planner might have laid down deliberately. It is none of those things. It is a horizontal fluid pathway that hardened into stone. What makes this especially striking is the scale of the process. The formations at Zakynthos cover an area of several hundred square metres. That is a large area for a single geological process to have operated across, but it is not unusual for orthogenic carbonate systems. The fluid migration that drives them can affect large regions of seafloor, particularly in tectonically active areas where fracture networks are extensive and the supply of hydrocarbons from depth is substantial. The Ionian Sea, as will become clearer shortly, is exactly the kind of place where such conditions exist. There is also something worth noting about the uniformity of the material across the site, the total consistency and composition that the investigators had flagged as incompatible with human construction. In the context of orthogenic carbonate formation, that uniformity makes complete sense. A single geological process, operating under consistent chemical conditions across the whole area, produces consistent material throughout. There is no variation because there was no variation in the process. Every part of the site formed the same way, from the same fluids, through the same chemistry, producing the same dolomite. The uniformity that ruled out human construction is precisely what confirms the geological explanation. The process itself is not unique to Zakynthos. Orthogenic carbonate formations associated with hydrocarbon seeps have been documented in many places around the world. In the North Sea, carbonate mounds and concretions associated with methane seepage have been mapped and studied for decades, partly because of their relevance to the oil and gas industry, which needs to understand the behaviour of hydrocarbons in the seafloor. In the Black Sea, large carbonate structures have been found at active cold seep sites, some of them forming chimneys and mounds that rise several metres above the surrounding seafloor. Off the coast of California, in the Santa Barbara Channel, orthogenic carbonates associated with natural hydrocarbon seeps form hard substrate on the seafloor that supports rich biological communities. In the Gulf of Mexico, cold seep carbonate mounds have been extensively documented, some of them covering areas of many square kilometres, with structures ranging from flat pavements to irregular mounds to chimney-like columns. What distinguishes the Zakynthos site is not the process itself, which is geologically widespread, but the particular combination of shapes it produced, shapes that happened to align so precisely with the visual vocabulary of human architecture that they fooled, at least initially, everyone who saw them. That alignment is partly a matter of scale. The Zakynthos formations are sized roughly like architectural elements. The columns are roughly the diameter and height of ancient Greek columns. The ring formations are roughly the diameter of well foundations or column bases. If they were much larger or much smaller, they would not read as architectural. But at the scale they happen to have formed, in the particular shapes that the local fluid geometry produced, they sit almost exactly in the range of what a human builder might have constructed. That is a coincidence, in the strict sense of the word, a coincidence of scale and geometry. And it is, depending on how you look at it, either an extraordinary piece of bad luck for anyone hoping to find a lost city, or an extraordinary piece of good luck for anyone who finds the natural world interesting. The researchers who analysed the site in 2016 were careful to explain not just what the formations are, but why the specific shapes formed here, in this particular way. The crystal structure of the dolomite, examined under microscopy, showed the characteristic fabric of in situ precipitation. The crystals had grown in place, oriented by the local chemical environment, not shaped by any external force. The geochemical signatures of the material matched what would be expected from methane-derived orthogenic carbonate, with carbon isotope ratios that reflected the biological and thermogenic origin of the hydrocarbons involved. These are not visual observations, they are measurements, and measurements are harder to argue with than impressions. One of the things the study made clear is that the seep activity responsible for the formations was not recent. The dolomite had formed over a long period of geological time, under conditions that no longer exist at the site in the same way. The formations are, in a sense, a record of a past episode of fluid seepage, a snapshot of a process that operated here, hardened into stone, and then stopped, or at least changed. The seafloor around them continued to evolve, sediment shifted, sea levels changed. The softer material that once surrounded the dolomite structures eroded away, leaving the harder formations exposed, standing proud of the seafloor in the way that any erosion-resistant material eventually stands proud of its surroundings when everything softer around it has been worn away. This is actually a common pattern in geology. Hard rock, whatever its origin, tends to outlast soft rock. Erosion is selective. It takes the weak material first and leaves the strong material behind. At Zakynthos, the dolomite is the strong material. It survived while the surrounding sediment did not, and the result is a set of structures that appear to have been built up above the seafloor, when in fact they were always in the seafloor. They simply became visible as everything around them was gradually removed. There is something almost patient about that process. The dolomite did not appear suddenly. It did not erupt from the seafloor or fall from somewhere. It grew slowly in the dark, in the spaces between sediment grains, following the paths of fluids that were themselves following the paths of least resistance through fractured rock. And then it waited, for however long it took for the surrounding sediment to erode away, and then it was there, sitting on the seafloor in shallow water, in the clear Ionian light, looking for all the world like the ruins of something that people had built and lost. The tectonic context that made all of this possible, the specific geological setting of the Ionian Sea that supplied the hydrocarbons and the fracture networks that let them migrate, is a story in itself, and it is a story that goes back millions of years to a time when the region around Zakynthos looked nothing like it does today, and when the forces shaping it were operating on a scale that makes human history feel very brief by comparison. Understanding that context helps explain not just why the formations exist, but why they exist here, in this particular part of the Mediterranean, and what was happening beneath the seafloor when the dolomite was crystallizing in the dark. So let us stay with the shapes for a moment, because the shapes are really the heart of the story. Everything else, the media coverage, the tourism interest, the Atlantis comparisons, all of that flows from the fact that these formations look the way they look. And understanding how they got that way requires thinking about something that is not immediately intuitive: the geometry of fluid moving through rock. When a liquid or a gas moves through solid material, it does not move randomly. It follows paths. It finds cracks, pores, weak zones, boundaries between different types of sediment. It moves along the paths of least resistance, which in a layered seafloor are often very specific. A vertical fracture here, a horizontal boundary between sediment layers there. The fluid does not spread evenly in all directions the way it might in open water. It is constrained by the structure of the material it is moving through, and that constraint shapes everything that happens next. In the case of the Zakynthos formations, the hydrocarbon-rich fluids rising from below are moving upward through the seafloor sediment along specific conduits. Think of these conduits as narrow pipes or channels. Not literal pipes, but zones of higher permeability through which the fluid preferentially moved. Where a fluid rises through a single, roughly cylindrical conduit, the mineral precipitation that forms around that conduit takes on the shape of the conduit itself. The dolomite crystallizes outward from the walls of the channel, filling in and hardening the surrounding sediment in a roughly cylindrical form. When the softer sediment around it eventually erodes away, what remains is a cylinder of hard dolomite, a column. Not a column that anyone carved or placed, but a column nonetheless. A column produced by chemistry following geometry. The donut shapes, the circular ring formations, form through a slightly different but related process. When a fluid rises to a point in the sediment and then begins to spread outward radially, moving away from the central conduit in all directions at once, the precipitation front forms a ring. The chemistry happens at the boundary between the upwelling fluid and the surrounding pore water in the sediment, and because the fluid is spreading outward from a central point, that boundary is circular. The dolomite forms along that circular front, and over time it builds up into a ring or disc shape. Some of the formations at Zakynthos have this concentric quality: rings within rings, or a central column surrounded by a broader disc, which reflects the layered history of fluid seepage at that point, with different episodes of fluid flow leaving their mark at different radii. The flat surfaces, the ones that look most like paving stones or courtyard floors, form when fluid spreads laterally through a horizontal layer in the sediment, a thin, permeable bed sandwiched between less permeable layers above and below. The fluid moves through this layer the way water spreads through a sheet of wet sand, and as it moves, it precipitates dolomite uniformly through the layer. When the softer sediment above and below eventually erodes away, what is left is a flat, hard slab, sometimes cracked into polygonal shapes by later stress, sometimes relatively intact. From above, in clear shallow water, a flat dolomite slab looks almost exactly like a paved surface. The resemblance is not accidental in the sense of being random. It is a direct consequence of the geometry of horizontal fluid flow through a horizontal layer, which naturally produces horizontal flat surfaces. What makes this particularly striking is that these three basic shapes, vertical cylinders, circular rings, and flat horizontal slabs, are also the three basic elements of ancient Greek architecture. A Greek temple consists of columns, column bases, and paved floors. Those elements exist in Greek architecture because they are structurally logical responses to the problem of holding up a roof. You need vertical supports, you need stable bases for those supports, and you need a flat surface to build on. But the Zakynthos formations arrived at the same three shapes through an entirely different logic, the logic of fluid dynamics and mineral chemistry, and the result is a set of structures that sit almost perfectly within the visual vocabulary of ancient construction. It is worth pausing on that for a moment, because it is genuinely strange. Two completely unrelated processes, one involving human beings cutting and placing stone, the other involving methane seeping through sediment millions of years ago, produce shapes that are nearly indistinguishable to the eye. That is not a trick. That is not an illusion. The shapes really are similar. The similarity is real. What is not real is the inference that similar shapes must have similar causes. The surrounding sediment that once enclosed these formations has, over a very long time, been gradually removed by the movement of water, by biological activity, by the slow settling and resettling of the seafloor. Dolomite is harder and denser than the surrounding sediment, so it resists erosion more effectively. As the softer material erodes, the dolomite remains. This is a process geologists sometimes describe informally as differential erosion, and it happens everywhere that hard and soft materials exist side by side. A harder layer of rock in a cliff face will protrude as the softer rock around it is worn back. A harder nodule in a riverbed will remain as a bump long after the surrounding rock has been smoothed away. At Zakynthos, the dolomite formations are the harder material, and they now stand above the surrounding seafloor because everything softer has been removed from around them. This is why they appear to have been built up above the ground, the way ruins appear to stand above the surrounding soil. Real ruins look that way because their foundations were buried over time, and the upper portions remain exposed. The Zakynthos formations look that way because the opposite happened. The material around them was removed rather than added. The visual result is similar. Hard structures rising above a softer surrounding surface, but the process is the reverse. Similar orthogenic carbonate structures have been documented in many parts of the world, and some of them are worth mentioning because they help establish that what happened at Zakynthos is not an isolated quirk, but a recognisable geological phenomenon. In the North Sea, carbonate concretions and mounds associated with methane seepage have been studied extensively, partly because the oil and gas industry has practical reasons to understand how hydrocarbons behave as they migrate through the seafloor. Some of these North Sea structures have been cored and analysed in detail, and their internal fabric, the crystal structure of the carbonate, the isotopic signatures of the carbon, closely matches what was found at Zakynthos. In the Black Sea, active cold seep sites have produced carbonate structures that rise several metres above the surrounding seafloor, some of them forming irregular chimneys and mounds, others forming flatter pavements. These Black Sea structures are associated with ongoing methane seepage and support communities of specialised organisms adapted to the chemical environment around the seeps. Off the coast of California, in the Santa Barbara Channel, and in other areas along the Pacific margin, orthogenic carbonates form hard substrate on the seafloor at natural hydrocarbon seep sites. These formations are well known to marine biologists because they provide stable hard surfaces in an otherwise soft sediment environment, and the biological communities that colonize them are distinctive and well studied. In the Gulf of Mexico, cold seep carbonate mounds have been documented across large areas of the deep sea floor, some covering many square kilometres, with structures that range from flat pavements to irregular mounds to chimney-like columns rising from the seafloor. The Gulf of Mexico examples are particularly well documented because the region has been intensively surveyed for oil and gas resources, and the seep carbonates are a recognised feature of the seafloor geology. What distinguishes the Zakynthos site from most of these other examples is, again, the particular combination of shapes, the way the local fluid geometry happened to produce forms that align so closely with architectural elements. Most orthogenic carbonate structures, when you look at them, are clearly geological. They are irregular, lumpy, asymmetrical in ways that do not suggest any particular pattern. The Zakynthos formations are unusual because the local conditions, the specific arrangement of fractures and permeable layers in the sediment, the particular way the fluids were moving, produce shapes that are unusually regular and unusually close in scale to human construction. That regularity is real, and it is a product of the regularity of the underlying fluid flow patterns. Fluids moving through consistent fractures produce consistent shapes. The seafloor at Zakynthos apparently had a fairly regular fracture pattern, and a fairly consistent set of permeable layers, and the result was a set of formations that are more geometrically regular than most seep carbonates elsewhere. The 2016 study, published in Marine and Petroleum Geology, was careful to address this regularity directly. The researchers did not simply say that the formations were natural and leave it at that. They explained, through the petrographic and geochemical analysis, specifically how the shapes formed, which fluid pathways produced which structures, and why the dolomite crystallized in the particular geometries it did. The explanation is grounded in measurements, not just visual assessment. The carbon isotope ratios, the crystal fabric visible under the microscope, the absence of any biological or cultural material in the matrix of the stone. These are not matters of interpretation in the way that visual impressions are. They are data, and the data pointed clearly in one direction. There is something satisfying about that in a quiet way. The question of what these formations are was not settled by someone looking at them and deciding they did not look artificial enough. It was settled by analysing the material itself, by asking the stone what it was made of and how it grew, and the stone answered clearly. That is what scientific investigation at its best actually does. It does not override perception with authority. It provides a different kind of evidence, one that goes deeper than what the eye can see. And the answer the stone gave is, in its own way, remarkable. Dolomite crystallizing in place over millions of years, following the paths of fluids that were themselves following the paths of fractures in ancient rock, building up slowly in the dark sediment of a shallow marine environment that no longer exists in the same form. That is a story with its own kind of depth. It does not have the drama of a lost civilization, but it has something else. A sense of deep time, of processes operating on scales that are genuinely hard to hold in the mind, of a planet that is constantly building and eroding and rearranging itself according to rules that have nothing to do with human history and everything to do with chemistry and physics, and the slow movement of tectonic plates. The formations at Zakynthos are, in a sense, a message from a much earlier version of this part of the world, a record of conditions that existed here millions of years ago, when the Ionian Sea looked different, when the seafloor was at a different depth, when the fracture patterns in the rock were channeling different fluids in different ways. The dolomite preserved that record in stone, and the subsequent erosion of the surrounding sediment uncovered it. And then in 2013, a snorkeler floated over it in clear shallow water and saw what looked like a lost city. The chain of events that led from ancient fluid seepage to that moment of misrecognition is, if you think about it, genuinely extraordinary. Not because the formations are ruins, but because they are not, and because the process that actually made them is older and stranger than any human city could be. All of that geological history, the fluids, the fractures, the crystallization, the erosion, took place within a specific tectonic setting, and that setting is itself part of the story. The Ionian Sea is not a quiet, geologically stable place. It sits within one of the most seismically active regions in Europe, shaped by forces that are still operating today, forces that influence not just the existence of the Zakynthos formations, but the specific character of the seafloor environment in which they formed. To understand why these structures exist here, in this part of the Mediterranean and not somewhere else, it helps to understand what is happening beneath the seafloor of the Ionian Sea, what has been happening there for millions of years, and what continues to happen now. The Ionian Sea sits at the western edge of the Aegean world, and it is, by almost any geological measure, one of the most restless bodies of water in Europe. Not restless in the way that the North Atlantic is restless, with storms and swells and the drama of surface weather. The Ionian's restlessness is deeper than that. It is structural. It is built into the foundation of the seafloor itself, into the geometry of the plates that meet and grind and slide beneath it, producing forces that have been reshaping this part of the Mediterranean for tens of millions of years and show no particular sign of stopping. Zakynthos sits near the Hellenic subduction zone, which is one of the more consequential tectonic boundaries in the region. Here, the African plate, moving slowly northward, as it has been doing for a very long time, slides beneath the Eurasian plate. The process is called subduction, and it is exactly what it sounds like. One plate descending beneath another, pushing down into the mantle, generating heat and pressure, and a continuous supply of geological consequences at the surface. Subduction zones produce earthquakes, they produce volcanic activity, and they produce something else that is directly relevant to the Zakynthos story. They drive the movement of fluids through the crust. As the African plate descends, it carries with it sediments that were deposited on the seafloor over millions of years, sediments that contain water, organic material, and hydrocarbons in various forms. As those sediments are compressed and heated during subduction, they release fluids. Those fluids have to go somewhere, and they tend to migrate upward through whatever fractures and permeable pathways are available in the overlying crust. In a region like the Ionian, where the crust has been deformed and fractured by millions of years of tectonic activity, there are plenty of pathways. The result is a seafloor that is, in places, actively venting fluids, water, methane, carbon dioxide and other compounds, up through the sediment and into the water column above. This is the geological context in which the Zakynthos formations came to exist. The fluids that produced the dolomite, the methane-rich fluids that reacted with the surrounding sediment and caused carbonate minerals to precipitate in place, were not some isolated local phenomenon. They were part of a much larger system, driven by the same tectonic forces that produce earthquakes on Zakynthos and that have been shaping the Ionian seafloor since long before any human civilization existed in the region. The formations at Alicanas are in this sense a surface expression of something very deep, a visible record of processes that operate far below the seafloor at depths and pressures that are difficult to imagine from the surface. The age of the formations is estimated to fall within the Pliocene epoch, which ran from roughly 5 million to about 2.5 million years ago, though some estimates place the formation period somewhat more broadly, from around 2 to 5 million years before the present. The Pliocene was a time when the Mediterranean region looked quite different from how it looks today. Sea levels were not the same, coastlines were in different positions, the shallow marine environments of the Ionian were distributed differently across the landscape. The area where the Zakynthos formations now sit on the seafloor was, at the time of their formation, likely a shallow coastal or nearshore marine environment. The kind of setting where seafloor sediments accumulate steadily, where organic material is buried and begins to break down, and where the conditions for hydrocarbon generation and fluid migration are favourable. What this means, practically speaking, is that the dolomite structures did not form on the seafloor as it exists today. They formed in sediment that was, at the time, part of a different version of this coastline. The stone crystallized in place within that sediment, hardening slowly over geological time as the fluids moved through and the minerals precipitated. The surrounding sediment remained softer, more easily eroded. And then, over the subsequent millions of years, things changed. Sea levels rose and fell. The Ionian coastline shifted. Sediment was rearranged by currents and by the repeated seismic disturbances that are a permanent feature of this region. Gradually, the softer material around the dolomite structures eroded away, and the harder formations were left standing, exposed on the seafloor, projecting upward from the surrounding sediment, looking for all the world like something that had been placed there deliberately. The exposure of the structures is itself a geological process, not a sudden event. It happened incrementally, over a long span of time, as erosion slowly stripped back the sediment layer by layer. By the time a snorkeler floated over them in 2013, the formations had been sitting on the seafloor, in roughly their current condition for an unknown but probably substantial period. Long enough for them to be colonized by marine organisms, long enough for the seafloor around them to have settled into a new equilibrium. But in geological terms, their exposure is relatively recent. The dolomite itself is millions of years old. The moment of its becoming visible to the water above is much more recent than that. It is worth pausing on those timescales for a moment, because they are genuinely hard to hold in the mind. 2 to 5 million years ago is not ancient history in the way that ancient Greece is ancient history. Ancient Greece, even at its most remote, the Mycenaean period, the Bronze Age settlements that predate the classical world by more than 1,000 years, is roughly 3,000 to 4,000 years in the past. The Zakynthos formations are somewhere between 500 and 1,000 times older than that. They predate not just human civilization in Greece, but human civilization anywhere. They predate Homo sapiens entirely. They formed in a world that had no humans in it at all, a world where the Mediterranean coastline was populated by animals and plants that would be largely unrecognizable today in an ecological and climatic setting that has no direct parallel in the present. When you look at the formations in photographs, the pale dolomite rings and columns against the darker seafloor sediment, the way the light filters down through a few meters of clear Ionian water and catches the edges of the stone, it is easy to feel that you're looking at something human-scaled and human-timed. The structures are roughly the size of things that humans build. The columns are the height of columns in ancient temples. The rings are the diameter of courtyard features or cisterns. Everything about the scale feels familiar, feels like it belongs to the same world of human construction that you can find at archaeological sites all across Greece. That feeling of familiarity is part of what made the initial misidentification so natural and so immediate, but the familiarity is an illusion produced by coincidence of scale. The formations are not human-sized because humans made them. They are human-sized because the geological processes that made them, the diameters of fluid conduits, the thickness of permeable sediment layers, the geometry of fracture systems in the rock, happened in this particular place to produce structures at a scale that falls within the range of human construction. That is a coincidence, a remarkable one, but a coincidence nonetheless. The seismic history of the region adds another layer to the story. Zakynthos is not simply near a subduction zone in the abstract sense. It is one of the most earthquake-prone places in Europe in a very practical, experienced, documented sense. The island and its surrounding waters have been shaken repeatedly throughout recorded history, and the effects have been significant and sometimes devastating. The earthquake of August 1953 is the one that tends to anchor this history for most people who know anything about modern Zakynthos. It struck on the 12th of August with a magnitude of approximately 7.2, and it was followed within 2 days by a second major shock. The combined effect was catastrophic for the island. The town of Zakynthos, along with most of the island's villages, was almost entirely destroyed. Something like 90% of the buildings on the island collapsed. Hundreds of people died, and the subsequent fires that burned through the rubble made the destruction worse. The island had to be substantially rebuilt from almost nothing, which is why the town of Zakynthos today has a different architectural character from many other Greek island towns. It is a mid-20th century reconstruction rather than a layered accumulation of older buildings. The 1953 earthquake is mentioned here not because it had any direct effect on the dolomite formations. They are stone structures sitting in shallow water, and a seismic event, however severe, is unlikely to have dramatically altered them. But because it illustrates something important about the nature of this place. Zakynthos is not a stable, slowly changing environment. It is a place that gets violently rearranged on human timescales, let alone geological ones. The seafloor near the island has been shaken, shifted, and reshaped by earthquakes many times over the course of the millennia during which human beings have lived here. What the seafloor looks like today is not what it looked like 1,000 years ago, or 500 years ago, or even a century ago. The ongoing tectonic activity that drives the subduction zone beneath the Ionian is continuously modifying the physical environment of the region, both above and below the waterline. This matters for the formations because it means that the seafloor context in which they now exist is itself a product of ongoing geological change. The sediment around them has been disturbed by earthquakes. The fluid seep systems that originally produced them may have been modified or partially disrupted by seismic events over the millions of years since the dolomite formed. The rate of sediment erosion that exposed the structures has probably varied, with changes in sea level, current patterns, and the frequency and intensity of seismic disturbance. The formations as they exist today are not a pristine record of their original condition. They are a surviving remnant, the hardest, most resistant part of a geological system that has been continuously modified by the same forces that created it. There is something interesting in that thought. The dolomite survived because it is harder than the surrounding sediment. It resisted erosion precisely because the chemical process that formed it produced a material more durable than what was around it. The very mechanism that made the formations visible, the differential erosion that left the hard dolomite standing while the softer sediment was carried away, is a product of the same geological dynamics that have been operating in the Ionian for millions of years. The formations are visible today because the planet has been working on them for a very long time, and the planet's work, in this case, produced something that looks startlingly like the work of human hands. One of the things the 2016 study was careful to establish was not just the composition of the dolomite, but the specific geochemical signature that links it to a seep origin. Carbon isotope ratios in carbonate minerals can indicate something about the source of the carbon that went into them. Carbonates that form from methane-derived fluids, from the breakdown of organic material in sediment, the kind of process that happens in seep environments, tend to have distinctive carbon isotope ratios that differ from carbonates formed in other ways, such as from normal seawater chemistry or from biological shell material. The dolomite at Zakynthos showed isotope signatures consistent with a methane-derived or hydrocarbon-influenced origin, which is exactly what you would expect from orthogenic carbonate formed in a seep environment. That geochemical signature is not something that can be faked or confused with another process. It is a direct record of the chemistry of the fluids that were present when the mineral formed, preserved in the crystal structure of the stone itself. The stone carries its own history in its chemistry, and that chemistry tells a clear story about what kind of environment produced it. The tectonic setting also helps explain why this kind of formation exists here, and not in some more geologically quiet part of the Mediterranean. A passive, tectonically stable continental margin, the kind of seafloor you find along parts of the Western African coast, for example, or along some stretches of the Northern European shelf, does not typically generate the same kind of active fluid seepage that a subduction zone environment does. The compressional forces of subduction, the fracturing of the overriding plate, the migration of deep fluids upward through a deformed and permeable crust, these are conditions that are specific to tectonically active settings. The Ionian Sea has all of those conditions and has had them for a very long time. The Zakynthos formations are in part a product of their location, of the particular geological fate that placed this stretch of seafloor at the edge of a subduction zone, where the planet's interior is expressed at the surface in ways that include not just earthquakes and occasional volcanic activity, but also the quiet, slow chemistry of fluid seepage and mineral precipitation. What this all adds up to is a picture of the Zakynthos formations as something genuinely embedded in deep time, not in the poetic sense, but in a literal, measurable, geological sense. They are structures that formed millions of years ago in a different version of this coastline, driven by tectonic forces that are still operating today. They were buried in sediment for most of their existence. They were gradually exposed by erosion. They have been shaken by earthquakes many times. They now sit in a few meters of clear Ionian water, pale and geometric, looking for all the world like the remains of a courtyard or a colonnade, and they are none of those things. They're older than any human building on Earth. They were made by chemistry and pressure and time, not by hands or tools or any kind of intention, and yet they look the way they look. That is the fact that draws people to them, and that is the fact that makes this story worth telling. The appearance is real. The visual impression that struck the snorkelers in 2013 was not a delusion or an exaggeration. The formations genuinely do look like ruins. They look like ruins because of the specific geometry of fluid flow through fractured sediment, because of the way dolomite crystallizes around conduits and along permeable layers, because of the coincidence of scale, that place these geological structures in a size range that feels immediately familiar to human eyes. The appearance is a product of geology. The interpretation was a product of human perception. And the gap between those two things, between what the formations are and what they look like, is exactly where the interesting questions live. Those questions about perception, about why the human eye sees architecture in natural forms, about what it says about us that we so readily find evidence of civilization in the shapes that the planet makes on its own. Those questions are worth exploring in their own right. Because the snorkelers in 2013 were not being foolish or careless. They were doing something very human, something that is actually built into the way our brains process visual information, and understanding why the formations look so convincingly artificial turns out to require understanding something about human cognition that goes well beyond the geology of the Ionian seafloor. There is a concept in psychology called pareidolia. Most people have heard of it in the context of faces, the way a power outlet looks like a surprised expression, the way a knotted tree trunk resolves into a profile, the way clouds arrange themselves into animals or figures, or the suggestion of a face looking down. The brain, trained by a lifetime of social experience, is extraordinarily sensitive to the pattern of two eyes above a nose above a mouth, and it finds that pattern everywhere, even in textures and shadows that have nothing to do with faces. Pareidolia is usually explained as a byproduct of a useful skill. The ability to quickly recognize faces in ambiguous visual conditions, which is genuinely valuable in a social species, is so finely tuned that it occasionally misfires. The system is calibrated towards sensitivity rather than specificity. It is better to see a face that isn't there than to miss one that is. What happened at Zakynthos in 2013, and what happens every time a natural formation is mistaken for human construction, is something very similar to pareidolia, but operating on a different set of learned patterns. Humans don't just learn to recognize faces. We learn to recognize built environments. We spend our entire lives moving through spaces that were constructed by other people. Rooms with flat floors and vertical walls, streets with regular paving, columns holding up roofs, doorways cut at right angles, circular features like wells or amphitheatres or fountains. These patterns become deeply embedded in how we process visual information. A flat horizontal surface reads as a floor. A vertical cylinder reads as a column. Concentric rings read as a constructed feature. A well, a drain, a decorative element. Regularity and repetition read as intention. We don't have to consciously decide that something looks built. The recognition happens before the reasoning does. The Zakynthos formations hit nearly every one of these triggers at once. The cylindrical protrusions read immediately as columns. The flat, paved-looking surfaces read as floors or courtyards. The donut-shaped concentric rings read as architectural features. The base of a column, the surround of a well, the foundation ring of a circular structure. And these elements appeared together in the same area, at a consistent scale, in shallow, clear water, where the visibility was good and the light was bright, and the shapes could be seen whole. There was no obscuring depth, no murky water, no partial view that might have introduced ambiguity. The snorkelers at Alicana's Bay saw the formations clearly, and what they saw looked, with remarkable completeness, like the ruins of a built place. It is worth sitting with that for a moment, because it is easy to frame the story as one of foolish misidentification, as if the snorkelers should have known better, or as if the initial reports were somehow irresponsible. But that framing misses something important. The visual impression was not a failure of attention, or a failure of intelligence. It was the result of a perceptual system working exactly as it is designed to work, encountering a stimulus that happened to match its learned templates with unusual precision. The snorkelers were not wrong to be struck by what they saw. They were responding normally to a genuinely unusual visual situation. The formations do look like ruins. They look like ruins in a way that is not trivial or superficial, in a way that fooled not just casual swimmers, but also, at least briefly, people with considerably more experience looking at underwater sites. There are accounts suggesting that even some of the archaeologists and divers who first examined the site in person, before any detailed analysis had been done, found themselves pausing at the visual impression. The formations are not the kind of thing you look at and immediately think, no, obviously natural. They are the kind of thing you look at and think, this is strange, this is worth looking at carefully. That reaction, the pause, the second look, the sense that something needs to be explained, is exactly the right reaction. The problem is not the initial impression. The problem is when the initial impression becomes fixed before the investigation is complete. This particular kind of perceptual mistake has a long history, and the Zakynthos case is far from the only example. One of the most famous is the Bimini Road, discovered in 1968 off the coast of North Bimini in the Bahamas. A pilot named Robert Brush spotted it from the air, and a diver named Pino Daniele investigated it shortly afterward. What they found was a formation of large, flat limestone blocks arranged in a curved line on the seafloor, at a depth of about 5 to 6 meters, stretching for roughly half a mile. The blocks are roughly rectangular, some of them quite large, and they are arranged in a way that looks, unmistakably, like a paved road or pathway. The discovery came at a culturally charged moment, the late 1960s, when interest in Atlantis and alternative history was running particularly high, and it was quickly seized upon as possible evidence of a lost civilization, possibly even Atlantis itself, a claim that gained extra energy from the fact that Edgar Cayce, a popular American psychic, had predicted in 1938 that evidence of Atlantis would be found near Bimini around 1968 or 1969. Geological investigation of the Bimini Road has been extensive. The consensus among geologists is that the blocks are beach rock, a type of limestone that forms naturally when carbonate sediment is cemented together in the intertidal zone. Beach rock is known to fracture along regular lines, producing rectangular blocks that can look remarkably like dressed stone. The curved arrangement of the blocks is consistent with the natural shape of the ancient shoreline. Carbon dating of shells and organic material within the blocks placed their formation at around 3,000 years ago, during the Holocene, not during any period when a sophisticated civilization capable of road building was known to exist in the Bahamas. The geological case for a natural origin is strong, and yet the Bimini Road continues to attract visitors who believe it is artificial. It appears regularly in documentaries about Atlantis. The debate, in popular culture at least, is treated as ongoing, even though among the relevant scientific communities it largely is not. The reason the story has such staying power is partly about the visual impression. Those blocks really do look like a road, and partly about the cultural context that surrounded the discovery. Once a site has been framed as a possible lost city or a possible piece of Atlantis, that framing is very difficult to dislodge. It becomes part of the site's identity, part of the reason people visit it, part of the story that gets told about it. The scientific explanation, however thorough, is competing against a narrative that is simply more emotionally compelling. The case of Yonaguni, off the southwestern tip of Japan's Ryukyu Islands, is different in an important way, and it is worth comparing to Zakynthos because it represents a situation where the scientific question is genuinely more difficult to resolve. The Yonaguni monument was first noticed by a diver named Kihachiro Aratake in 1986, and it is considerably more dramatic than either the Bimini Road or the Zakynthos formations. The structure sits at depths ranging from about 5 meters to around 30 meters, and it is large, roughly 60 meters wide, 30 meters tall in some interpretations of the relief. It features what appear to be broad, flat terraces, right-angle cuts, parallel grooves running along the rock face, and formations that have been given names like the Turtle and the Stage. It is, visually, an extraordinary thing to encounter underwater. Masaki Kimura, a marine geologist at the University of the Ryukyus, argued for decades that the Yonaguni monument is a human construction, or at least a substantially human-modified natural feature. He pointed to what he described as tool marks, to the precision of certain angles, to features that he argued were too regular to be explained by natural processes. His position attracted significant attention, and Yonaguni became a fixture in discussions of lost civilizations and pre-Ice Age cultures. Robert Schoch, a geologist from Boston University who's best known for his controversial arguments about the age of the Egyptian Sphinx, took the opposing view. Schoch argued that the Yonaguni monument is entirely natural, a product of the way the local sandstone fractures. Yonaguni's bedrock is a type of fine-grained sandstone and mudstone that has a natural tendency to cleave along horizontal planes and to fracture along vertical joints, producing the kind of right-angle edges and flat surfaces that look to human eyes like deliberate cutting. Wave action, tidal currents, and the natural erosion of a rock with pronounced bedding and jointing, Schoch argued, could produce all of the features that Kimura was attributing to human hands. The important thing about Yonaguni, for the purposes of this story, is that the debate there is genuinely harder to settle than the debate at Zakynthos. The material at Yonaguni is sandstone, and sandstone genuinely can fracture into right angles. The question of whether specific features are natural or artificial is, in some cases, a matter of degree and judgment rather than a question that isotope chemistry or crystal fabric analysis can resolve cleanly. Some features at Yonaguni might be natural, some might be human modifications of natural features, and some might be entirely artificial, and distinguishing between those possibilities requires a level of detailed investigation that has not yet been conclusively completed. The site also sits in an area with a known history of human occupation going back thousands of years, and there are genuine questions about what the coastline looked like when sea levels were lower, during the last glacial maximum around 20,000 years ago. At Zakynthos, none of that ambiguity exists in the same way. The material is dolomite, not sandstone. Dolomite does not fracture into right angles under wave action. It forms through a completely different process, the chemical precipitation process described by the 2016 study. The geochemical signatures are specific and interpretable. The absence of any archaeological material, no pottery, no worked stone, no tool marks, no organic material associated with human activity, is total. The formations sit in a context where the geological explanation is not just plausible but detailed and testable, and where it has been tested. Zakynthos is not a case where reasonable scientists disagree about the interpretation. It is a case where the investigation produced a clear answer. The comparison to Yonaguni is useful precisely because it shows what a genuinely unresolved case looks like, and Zakynthos does not look like that. But the visual similarity between these sites, the way all of them produce the same initial impression of constructed space, of architecture, of human presence, points to something worth thinking about. The human perceptual system is not calibrated for the full range of things that the natural world can produce. We are calibrated for the range of things we encounter regularly, and we encounter natural geological formations far less often than we encounter built environments, at least in the direct close-up, this is right in front of me way that the snorkelers at Alicanas Bay encountered the Zakynthos formations. When something falls outside our calibrated range, when a geological process produces something that sits squarely within the visual template we use for built structures, the mismatch is not immediately apparent. The brain assigns the familiar category first, and the questioning comes later, if it comes at all. There is also something specific about the shallow depth of the Zakynthos formations that made them particularly susceptible to this kind of misidentification. 2 to 5 meters of water is very different from 20 or 30 meters. At 2 to 5 meters, in the clear light of the Ionian Sea, you can see the formations whole, in good resolution, without the colour distortion and low visibility that come with greater depth. The Mediterranean light at that depth is still bright, still warm, still close to what you would see in air. The formations appear in nearly the same visual conditions as a ruin on dry land would appear, which means the brain processes them with nearly the same set of assumptions it would bring to a surface site. There is no visual cue, no murkiness, no darkness, no distance. that signals this is a strange environment where normal rules might not apply. The clarity of the water, which is one of the things that makes the Ionian Sea so beautiful, was also one of the things that made the Zakynthos Formation so convincingly architectural. It is a small irony that the same conditions that made the site so visually striking, the shallow depth, the clear water, the good light, were also the conditions that made it accessible enough for the 2016 investigation to be conducted relatively straightforwardly. Researchers could work at those depths without specialised equipment. Samples could be collected, surfaces could be examined closely, the full extent of the formations could be mapped. The accessibility that made the misidentification easy also made the correction possible. What this all suggests, stepping back from the specific geology for a moment, is that the story of the Zakynthos underwater formations is not really a story about a mistake. It is a story about perception, about the way human visual cognition works, about the templates we carry for recognising built environments, about the specific conditions under which natural geology can trigger those templates so precisely that the initial impression is almost irresistible. The snorkelers in 2013 were not uniquely credulous or poorly informed. They were people whose brains were doing exactly what brains do, encountering a stimulus that fit the template for ancient ruins with remarkable fidelity. The interesting question is not why they thought it was a lost city. The interesting question is why the planet occasionally makes things that look so much like what we build. And that question, it turns out, opens into another one, about what it actually takes to move from a compelling initial impression to a settled scientific answer. Because the visual impression at Zakynthos was clear, and the scientific answer was also eventually clear, but the path between them required specific tools, specific kinds of analysis, a specific understanding of what kinds of evidence are actually diagnostic. The methodology that settled the Zakynthos question is worth understanding in its own right, not just as a footnote to the story, but as an example of how science actually works when it is applied carefully to a question that is genuinely interesting and genuinely uncertain. What exactly did the researchers do? And why did those particular methods produce a conclusion that the visual inspection alone could never have reached? So let us talk about Yonaguni for a moment, because it deserves more than a passing comparison. It is one of the genuinely fascinating unresolved questions in this whole area of study, and understanding what makes it unresolved, what keeps scientists and divers and researchers returning to it decade after decade, helps clarify why Zakynthos ended up in a different category entirely. The Yonaguni monument sits off the southern tip of Yonaguni Island, the westernmost point of Japan, closer to Taiwan than to the Japanese mainland. The island itself is small and remote, the kind of place most people have never heard of, and the underwater structure was not discovered through any organised scientific expedition. It was found in 1986 by a local diver named Kihachiro Aratake, who was exploring the waters near the island looking for hammerhead sharks, which are known to gather there in large numbers. What he found instead was something that stopped him cold. A massive stepped structure rising from the seafloor, its surfaces flat, its edges sharp, its geometry so regular that it looked, in his own words, like something built. The news spread through the diving community quickly, and within a few years the Yonaguni monument had become one of the most debated underwater sites in the world. The structure is large. That is the first thing to understand. It is not a collection of small formations you could walk past without noticing. The main platform is roughly 150 metres long, 40 metres wide, and rises about 27 metres from the seafloor, with its shallowest point sitting around 5 metres below the surface. The features that drew attention, and that continue to draw attention, include what appear to be broad, flat terraces arranged in a stepped pattern, like the side of a pyramid or a Mesoamerican temple. There are what look like right-angle cuts between levels. There are parallel grooves running across some surfaces. There is a feature that has been called the turtle, a large rounded shape that some researchers believe was deliberately carved. There are what appear to be holes, channels, and a long straight trench that runs along one side of the structure. photographs of the site are striking. Even knowing what you know going in, even approaching the images with full scientific skepticism, the geometry is arresting. It does not look like something you would expect to find on a natural seafloor. Two researchers became the central figures in the debate about Yonaguni, and their disagreement is instructive precisely because both are credentialed scientists working from the same physical evidence and reaching opposite conclusions. Masaki Kimura, a professor of marine geology at the University of the Ryukyus in Okinawa, spent years diving the site and became its most prominent advocate for a human origin. He argued that the right-angle cuts were too precise to be natural, that the parallel grooves showed evidence of tooling, that the overall plan of the structure was consistent with a ceremonial or civic building of some kind. He dated the structure to somewhere between 10,000 and 5,000 years ago, based on when sea levels in the region would have placed the site above water, and he connected it to the broader history of human settlement in the Pacific and East Asia during the late Pleistocene and early Holocene. His argument was not fringe speculation, it was a detailed, specific case built on extended direct observation of the site. Robert Schoch, a geologist from Boston University, who is perhaps better known for his controversial work on the age of the Sphinx in Egypt, examined Yonaguni and came to the opposite conclusion. He argued that the rock at Yonaguni is a fine-grained sandstone that has a strong natural tendency to fracture along straight planes. Sandstone of this type, when subjected to the mechanical forces of wave action, tidal currents, and the freeze-thaw cycles that affect shallow water rock, will naturally produce flat surfaces, right-angle breaks, and parallel fracture lines. The terraced appearance, he argued, is consistent with the natural erosion of a rock formation that already had a stepped internal structure due to its sedimentary layering. The grooves could be natural channels formed by water flow. The apparent precision of the angles reflects the crystal structure of the rock itself, not the work of human hands. Schoch did not dismiss the site as uninteresting. He found it geologically remarkable, but he was firm that there was no need to invoke human construction to explain what was there. What makes this debate genuinely difficult to resolve is that both arguments have real weight. The sandstone at Yonaguni does fracture along straight lines. That is a documented property of the rock, not a claim that requires special pleading. Natural sandstone formations in various parts of the world do produce flat terraces and angular geometry through erosion. On the other hand, some of the features at Yonaguni, certain holes, certain channels, certain specific configurations, are harder to explain through the natural fracturing model alone, and Kimura's detailed documentation of these features has not been fully refuted. The site has not been subjected to the same kind of comprehensive geochemical and petrographic analysis that was applied to Zakynthos. The material is different, the formation process would be different, and the diagnostic test that worked so clearly at Zakynthos would not necessarily be applicable in the same way. The question of whether some features at Yonaguni represent opportunistic human modification of a naturally formed rock structure, a kind of hybrid origin, has not been conclusively answered either way. It is possible to build on natural formations, to use what the rock already provides and enhance it. That possibility alone keeps the debate open in a way that is intellectually honest, even if it is also frustrating. There is also the question of sea level history. During the last glacial maximum, roughly 20,000 years ago, sea levels globally were about 120 metres lower than they are today. Yonaguni's shallowest features, at around 5 metres depth, would have been above water as recently as 10 to 12,000 years ago. That timing overlaps with the late Jomon period in Japan, a culture that was sophisticated enough to leave behind complex settlements, pottery, and evidence of maritime activity. The idea that people were present in the region and capable of modifying coastal rock formations during that period is not archaeologically implausible. It does not prove that they did, but it does mean the possibility cannot be dismissed on the grounds that no human population existed there at the relevant time. At Zakynthos, the geological timeline points to formation during the Pliocene, 2 to 5 million years ago, when there were no humans anywhere in the region. That difference in timeline matters enormously. A structure that formed millions of years before modern humans existed cannot have been built by humans. A structure that was above water 10,000 years ago, in a region with a documented human presence, exists in a very different category of possibility. The contrast between the two sites comes down to this. At Yonaguni, the material is consistent with natural fracturing, but some features remain difficult to fully explain through that mechanism alone. The geochemical analysis has not been completed at the level that would be diagnostic, and the timeline does not rule out human involvement. The debate is genuine, not because the evidence equally supports both sides, but because the evidence has not yet been assembled in a way that definitively closes either door. At Zakynthos, the evidence was assembled: the dolomite composition, the orthogenic carbonate geochemistry, the crystal fabric, the complete absence of archaeological material, the known presence of hydrocarbon seep activity in the region. These things together do not leave a comparable gap. They point in one direction, and the pointing is specific and testable, not just plausible. What is useful about holding both sites in mind at the same time is that it clarifies what a settled scientific question actually looks like, compared to an unsettled one. Both sites produced an initial impression of human construction. Both sites attracted serious researchers. Both sites generated public excitement and media coverage. But the outcomes of the investigations were different, not because the scientists at one site were more careful or more skeptical than the scientists at the other, but because the evidence at the two sites is genuinely different in its character and its completeness. Science does not always produce clean answers on the same timeline. Sometimes the evidence is there and accessible and interpretable, and the answer comes relatively quickly. Sometimes the evidence is partial, or the diagnostic tests have not been applied, or the material itself is ambiguous in ways that make interpretation genuinely difficult. Yonaguni is in the second category. Zakynthos ended up in the first. There is a version of this story that treats the Zakynthos resolution as somehow deflating, as the scientists arriving to take away the magic, and that version of the story has some emotional truth to it. The Lost City narrative is more immediately romantic than the methane seep narrative. Columns built by ancient hands carry a different kind of weight than columns precipitated by chemistry over millions of years. But there is something slightly off about that framing, because it assumes that the natural explanation is the lesser one, the consolation prize you accept when the exciting answer turns out to be wrong. That assumption is worth questioning. The Yonaguni debate remains open partly because the romantic interpretation, the lost city, the drowned civilization, is so compelling that it has motivated decades of diving and research and documentation that might not otherwise have happened. In that sense, the initial misidentification has been generative. It has produced a body of work about a genuinely interesting geological and potentially archaeological site that would otherwise have received far less attention. The same is true of Zakynthos. The Lost City story brought investigators to the site. The investigation produced the 2016 paper. The 2016 paper documented a specific and scientifically interesting example of orthogenic carbonate formation in a seismically active shallow marine environment. That documentation has value independent of the question that prompted it. The wrong question, pursued carefully, produced real knowledge. And the Yonaguni comparison does one more thing that is worth noting. It shows that the human tendency to see architecture in natural forms is not a failure of intelligence or a sign of credulity. It is a consistent, cross-cultural, cross-disciplinary response to a specific kind of visual stimulus. Trained geologists, experienced divers, professional archaeologists, all of them have paused at these sites and felt the pull of the architectural interpretation. The formations trigger something deep and consistent in human visual cognition, something that does not switch off when you have a PhD. The question is what you do with that initial impression, whether you follow it uncritically or whether you bring the right tools to bear and let the evidence speak in its own language, which is often quieter and more specific than the language of first impressions. At Zakynthos, the right tools were brought to bear. The evidence spoke clearly, and what it said was not, in the end, a lesser story. It was a different story, one that reaches back millions of years rather than thousands, one that involves the deep chemistry of the earth rather than the labour of human hands, one that is stranger and in some ways more difficult to picture than a drowned Greek city, but no less real for that. The methodology that produced that answer, the petrographic analysis, the isotope chemistry, the crystal fabric examination, the careful archaeological survey, is worth understanding in its own right, because it shows exactly how science moves from a compelling visual impression to a conclusion that can actually be trusted. And that is where the story goes next. So let us talk about what the investigation at Zakynthos actually looked like in practice, because the conclusion, natural formation, not human-made, did not arrive simply because a few researchers looked at the stones and made an educated guess. It arrived through a specific sequence of tests, each one asking a different question of the material, and each one returning an answer that pointed the same direction. That convergence is what makes the conclusion trustworthy. Not any single test, but the accumulation of them, the way they reinforce each other from different angles and through different methods. The starting point was petrographic analysis. When researchers collected samples from the formations, small cores and fragments of the dolomite, those samples were prepared as thin sections, which means they were ground down to a thickness of roughly 30 micrometers, thin enough that light can pass through the stone. Under a petrographic microscope, you're not just looking at the surface of a rock, you're looking inside it, at the arrangement of crystals, the way they interlock, the size and shape of individual mineral grains, the presence or absence of voids, the texture of the matrix. And what the thin sections from Zakynthos showed was a crystal structure entirely consistent with dolomite that had formed in place through slow mineral precipitation from fluid, rather than dolomite that had been quarried from a source rock and shaped by tools. This distinction matters more than it might initially seem. When you quarry stone and work it, you leave traces in the crystal fabric. Cutting, grinding and polishing all disturb the surface layer of a rock at the microscopic scale. The crystals at the cut face are fractured differently than the crystals deeper in the stone. There are also often traces of the tool itself, fine striations, pressure fractures, occasionally even metallic residue in later periods. None of that was present in the Zakynthos samples. What was present instead was a fabric of interlocking dolomite rhombs, the characteristic crystal shape of dolomite arranged in a pattern consistent with slow growth from a supersaturated fluid. The crystals had grown into each other over time, filling space the way crystals do when they form in a quiet chemical environment, rather than being cut from an existing mass of rock. Petrographic analysis told researchers what the stone was and roughly how it had formed, but it could not, on its own, tell them where the fluids that formed it had come from. For that, they turned to geochemical isotope analysis, which is a different kind of question asked through a different kind of instrument. Isotope analysis works by measuring the ratios of different isotopes of the same element within a sample. For carbonate minerals like dolomite, the most diagnostic measurements involve carbon and oxygen. Carbon has two stable isotopes, carbon-12 and carbon-13, and the ratio between them in a carbonate mineral carries information about the source of the carbon that went into building it. Oxygen isotopes similarly record information about the temperature and chemistry of the water from which the mineral precipitated. These ratios are not arbitrary. They fall into characteristic ranges depending on the process that produced the carbonate, and those ranges are well documented from decades of research on carbonate geology around the world. The carbon isotope values from the Zakynthos dolomite were significantly negative, what geochemists describe as depleted in carbon-13. This is a diagnostic signature, carbonates that form from methane-derived fluids, meaning fluids in which the carbon comes from the microbial or thermogenic breakdown of organic matter deep in the sediment, consistently show this kind of carbon isotope depletion. The reason is that methane itself is strongly depleted in carbon-13 relative to the heavier isotope, and when methane is oxidized by microbes near the seafloor, a process called anaerobic oxidation of methane, The carbonate that precipitates from that reaction inherits the isotopic signature of the methane. The Zakynthos samples matched this pattern closely. The carbon isotope values fell squarely within the range documented for methane-derived orthogenic carbonates from seep environments around the world. This is not a subtle or ambiguous result. Quarried limestone or marble, the kind of stone a human builder would use, has carbon isotope values in a completely different range, reflecting the marine carbonate from which it originally formed rather than the microbial processing of deeply buried organic matter. The gap between the two ranges is large enough that there is no realistic overlap. When you see the isotope values from the Zakynthos dolomite plotted against reference datasets, the samples cluster with cold seep carbonates, not with any kind of construction material. The oxygen isotope values added a complementary piece of information. They were consistent with precipitation from fluids at relatively low temperatures, which fits the shallow marine environment and the slow, long-duration precipitation process rather than anything involving high-temperature geological activity. The oxygen values also helped constrain the approximate conditions under which the dolomite formed, lending support to the broader picture of cold seep chemistry operating over an extended period of time. After the isotope work came scanning electron microscopy, which allowed researchers to examine the internal fabric of the dolomite at a much finer scale than optical microscopy permits. Scanning electron microscopy works by bouncing a focused beam of electrons off the surface of a sample and collecting the signals that return, building up an image at magnifications that can reach tens of thousands of times. At that scale, you can see individual crystal faces, the way crystals nucleate and grow, and the relationship between different phases of mineral in a complex rock. What the electron microscopy showed in the Zakynthos samples was a fabric of well-formed dolomite rhombohedra. That is the technical term for the characteristic crystal shape of dolomite, growing in a pattern that indicated slow, undisturbed precipitation from solution. There was no evidence of mechanical stress, no fracture patterns associated with cutting or shaping, and no foreign material embedded in the crystal surfaces that would suggest contact with metal tools or human-made substances. The electron microscopy also allowed researchers to look at the porosity structure of the dolomite, the tiny spaces between crystals, and to assess whether those spaces contained any biological or cultural material. They did not. In a genuine archaeological site, even a very old one, the matrix of sediment and stone often contains organic fragments, plant material, charcoal, bone, shell, the chemical traces of decomposed biological matter. The Zakynthos samples were clean in this regard. The matrix was mineralogically simple, consistent with a purely inorganic formation process. Then there was the archaeological survey itself, which ran alongside the laboratory analysis. And this part of the investigation is worth dwelling on for a moment, because it is easy to underestimate how thorough a proper underwater archaeological survey actually is. The team did not simply swim over the formations and note the absence of obvious artifacts. They conducted a systematic examination of the seafloor across the site and in the surrounding area, looking for pottery sherds, which survive underwater for thousands of years and are the most reliable indicator of human habitation, as well as coins, worked bone, glass, metal objects, and any evidence of construction joints, mortar or tool marks on the stone surfaces themselves. Nothing was found, not a single sherd, not a coin, not a fragment of worked bone or metal, no mortar, no tool marks visible to the naked eye or under magnification. This absence is significant in a specific way. Genuine ancient Greek or Roman underwater sites, and there are many of them in the Mediterranean, are almost always accompanied by artifacts. The submerged portions of ancient Baiae in the Bay of Naples contain mosaic floors, marble statues, lead pipes, and pottery in abundance. Pavlopetri off the Laconian coast, the Bronze Age underwater town mapped in detail starting in 2009, contains pottery dating to roughly 2800 BCE and architectural features with clear construction joints and differentiated building materials. Alexandria's submerged royal quarter has yielded sphinxes, column bases and statuary. Human sites leave human things behind. They leave the residue of daily life, of construction, of the objects that people made and used and dropped and lost. The Zakynthos formations left none of that, across an area of several hundred square metres, in water shallow enough to survey thoroughly. The 2016 paper in Marine and Petroleum Geology, authored by Professors Ioannis Iliopoulos, Julian Andrews and their colleagues, laid all of this out in careful detail. The paper is not a dramatic document. It reads the way scientific papers read, methodically, with extensive reference to comparative literature, with caveats where caveats are appropriate, and with conclusions stated in measured language. But the conclusions are clear. The formations at Zakynthos are natural. They formed through the microbially mediated anaerobic oxidation of methane seeping from the seafloor, a process that caused dolomite to precipitate within the sediment. The shapes, the columns, the rings, the flat surfaces, reflect the geometry of fluid flow through the sediment, not the intentions of a builder. The isotopic and petrographic evidence is consistent with this interpretation and inconsistent with any hypothesis involving quarried or worked stone. What makes this a strong scientific conclusion, rather than simply a plausible opinion, is precisely that convergence of independent lines of evidence. Each test, petrographic, isotopic, crystallographic, archaeological, approached the question from a different direction and through a different methodology. Each one produced results consistent with the natural seep hypothesis and inconsistent with the human construction hypothesis. When independent lines of evidence converge on the same answer, that convergence is the scientific community's best available tool for distinguishing well-supported conclusions from speculation. It does not produce absolute certainty. Nothing in empirical science does, but it produces something considerably more reliable than any single test could provide on its own. It is also worth noting what the researchers did not do, because restraint is part of good methodology too. They did not claim to have identified the specific seep conduits that produced the formations. They did not attempt to date the formations with a precision beyond what the available evidence supported. They noted that the broader geological context, the Hellenic subduction zone, the documented history of hydrocarbon seepage in the Ionian region, was consistent with their interpretation, without claiming that consistency is proof. The paper is honest about the limits of what it can establish, and that honesty is part of what makes it credible. Comparable orthogenic carbonate structures have been documented in enough other locations that the Zakynthos formations do not require any special pleading. Cold seep carbonates with similar morphologies, columns, mounds, flat crusts, concentric rings, have been described from the Gulf of Mexico, from the Norwegian margin, from the Black Sea, and from sites off the California coast. The process is well understood. The shapes it produces are well documented. The Zakynthos formations fit within that documented range in terms of their chemistry, their crystal fabric, and their morphology. They are an example of a known phenomenon in an unusual location, shallow enough to be seen by snorkelers, clear enough to be photographed, regular enough to look, at first glance, like something built. That last point is perhaps the most interesting one from a purely scientific perspective. Most cold seep carbonate formations occur at depths of hundreds or thousands of meters, far below the reach of casual observers. The Zakynthos formations sit at 2 to 5 meters. They are in a sense an unusually accessible example of a process that normally operates in the dark, at pressure, invisible to anyone without specialized equipment. The fact that they were noticed at all, and noticed so dramatically, and investigated so thoroughly, is partly a consequence of their shallow depth and their location in a heavily visited tourist area. A similar formation at 500 meters depth would have been found eventually by oceanographic survey equipment, documented in a technical paper, and attracted no public attention whatsoever. There is something slightly accidental about the whole story then. a snorkeler swimming in clear, shallow water over a formation that looked like a courtyard, a photograph that spread quickly, a media cycle that latched onto the most romantic possible interpretation, and then, eventually, a careful scientific investigation that replaced the romance with something more precise and more durable. The romance was the catalyst. The investigation was the substance, and the substance holds up. What it does not do entirely is satisfy everyone, because even a methodology this careful, this convergent, this well-documented, does not always succeed in changing the minds of people who arrived at the question with a strong prior attachment to a particular answer. The Lost City narrative was out in the world before the 2016 paper existed. It had circulated in headlines and social media posts and travel articles and YouTube videos. It had become part of how some people thought about Zakynthos, part of the story they associated with the island, part of what made the place feel special. And a scientific paper, however rigorous, does not automatically reach the same audience that a viral photograph reaches. The paper was published, the conclusion was clear, and the Lost City story kept circulating anyway, because stories move differently than evidence does, and because the emotional logic of a drowned civilization is simply more immediately compelling than the chemical logic of a methane seep. That gap between what the evidence shows and what the narrative continues to claim is its own kind of interesting problem, and it says something about how information travels and how myths persist even in an age when the relevant scientific literature is freely accessible to anyone who looks for it. And that gap is worth sitting with for a moment, because it is not a simple problem. It is tempting to frame it as a matter of misinformation, of people stubbornly refusing to accept what the evidence shows. But the reality is a little more layered than that, and a little more human, and understanding it requires thinking about something older than social media or viral photographs or even the 2013 snorkeler reports. It requires thinking about Plato. Around 360 BCE, the Athenian philosopher wrote two dialogues, the Timaeus and the Critias, in which a character named Critias relays a story supposedly passed down through generations from the Athenian statesman Solon, who had heard it from Egyptian priests. The story described Atlantis, a powerful island civilization located beyond the Pillars of Hercules, which is to say beyond the Strait of Gibraltar in the Atlantic Ocean. This civilization had been, according to the account, extraordinarily advanced, extraordinarily wealthy, and extraordinarily corrupt, and the gods had punished it by sinking it beneath the sea in a single day and night. Plato used the story as a moral and political parable. Whether he intended it as literal history, invented allegory, or something in between has been debated by scholars for more than 2,000 years, and there is no consensus. What is clear is that the story lodged itself in Western imagination with a persistence that no other ancient myth quite matches. Atlantis is not just a lost city. It is the lost city, the archetype against which all other submerged or vanished civilizations are measured. The reason the Atlantis myth has this particular grip is not hard to understand. It combines several things that human beings find deeply compelling in a single package. There is the idea of a civilization more advanced than we expected, which flatters our sense that history is longer and richer than the official record admits. There is the idea of catastrophic loss, which resonates with something elegiac in human nature, the sense that great things are fragile and that the world contains absences where something magnificent used to be. There is the inaccessibility of the ocean, which protects the myth from easy falsification, because the sea is large and deep and most of it remains unmapped in fine detail. And there is the specific image of ruins beneath water, which is visually and emotionally unlike any other kind of ruin. A ruined building on land has been exposed to weather, to vegetation, to centuries of human interference. A ruined building beneath the sea feels preserved, sealed, waiting. The water feels like a kind of preservation, even though in reality the sea is not gentle to structures at all. This emotional logic is what the Zakynthos formations walked into in 2013. They did not need to look exactly like a city. They just needed to look enough like a city in the right context to activate the Atlantis-shaped space that already existed in the imagination of anyone who had ever heard the story, and almost everyone has heard the story. The columns, the rings, the flat paved-looking surfaces in clear shallow Mediterranean water off a Greek island in a sea that genuinely does contain real underwater ruins. The conditions were almost perfectly arranged to make the romantic interpretation feel not just possible but obvious. The snorkeler who first photographed those formations and thought they had found something extraordinary was not being foolish. They were being human in the most understandable way. The media cycle that followed was also, in its own way, behaving predictably. News organisations are not primarily in the business of waiting for scientific confirmation before reporting on interesting things. They are in the business of capturing attention, and a possible lost Greek city discovered by snorkelers captures attention in a way that a geological survey of methane seep carbonates does not. The headlines that appeared in 2013, Lost City discovered off Greek island, ancient ruins found underwater near Zakynthos, and yes, in some outlets, variations on the word Atlantis, were not invented from nothing. They were describing something real that people had genuinely found and genuinely found remarkable. The framing was wrong, but the excitement was not entirely manufactured, and once a story is circulated in that form, with that framing, it becomes very difficult to replace. The correction rarely travels as far as the original claim. This is not a new observation. It has been documented in the context of political misinformation, medical rumours, and historical myths for decades. But it applies here with particular clarity. The 2016 paper in Marine and Petroleum Geology was published 3 years after the initial reports. 3 years is a long time in terms of how a story settles into public memory. By 2016, the Zakynthos Lost City had already appeared in travel articles, in listicles about mysterious underwater discoveries, in YouTube videos about ancient civilizations, and in at least a few books about Atlantis and related topics. The scientific paper appeared in an academic journal that the vast majority of people who had seen the original headlines would never read, or even know existed. The paper was covered by some science journalists, and those articles reached some portion of the audience that follows science news. But the original Lost City framing had already reached a much larger audience, had already been shared far more widely, and had already been incorporated into the mental furniture of a lot of people who simply never encountered the correction. This is not unique to Zakynthos. The Bimini Road, a formation of flat limestone blocks discovered in shallow water off North Bimini in the Bahamas in 1968, has been the subject of geological analysis that consistently supports a natural origin. The blocks are beach rock, a type of sedimentary formation that develops when sand and shell material is cemented together by calcium carbonate in the intertidal zone. Beach rock commonly fractures along regular lines, producing the kind of flat, rectangular blocks that the Bimini Formation consists of. Geologists have documented this explanation thoroughly, and yet the Bimini Road continues to appear in books and documentaries about Atlantis, continues to attract divers who believe they're swimming over the remains of a lost civilization, and continues to be described in terms that ignore or dismiss the geological consensus. The explanation did not kill the myth. It ran alongside the myth, and the myth has more emotional momentum. There is a tourism dimension to this persistence as well, and it would be naive to ignore it. Zakynthos is a Greek island that depends significantly on tourism. It is beautiful, it has beaches and clear water and good weather, and it has a reasonable claim on visitors' attention without any help from lost civilizations. But a possible ancient underwater city adds something that beaches and weather cannot quite provide, which is the specific thrill of mystery, the sense that this particular place might be connected to something vast and vanished and significant. Local businesses, travel writers, and tourism promoters are not necessarily invested in the geological truth of the formations. They are invested in what brings people to the island, and the lost city story brings people to the island. It is not cynical to acknowledge this. It is simply true that economic interests and romantic narratives often reinforce each other, and that both are more immediately motivating than a paper in a geology journal. Social media has extended this dynamic in ways that were not possible in earlier decades. A photograph of the Zakynthos formations, posted with a caption suggesting ancient ruins, will be shared and liked and commented on in ways that a link to a scientific paper about orthogenic carbonate formation simply will not be. The visual quality of the formations is genuinely striking. They photograph well. They look, in a still image, exactly like what people imagine ruins should look like. And still images on social media platforms are not accompanied by footnotes or corrections or links to the relevant scientific literature. They circulate as images, with whatever caption was attached to them, and the caption is usually the one that was written when the story first broke, not the one that would be accurate given what the science has since established. None of this is to say that the people who continue to find the Lost City interpretation compelling are acting in bad faith. Most of them simply encountered the story in one form and never had a reason to seek out its later resolution. The information environment they moved through did not surface the correction in a way that was as vivid or as emotionally compelling as the original claim. This is a structural problem, not a personal one. And it is worth being honest about the fact that the scientific explanation, while correct, is also genuinely less immediately exciting to most people than the idea of a drowned Greek city. Methane seep carbonates are fascinating if you already have some context for why they are fascinating. If you do not, they sound like a technical explanation designed to take something wonderful away from you. But here is the thing, and it is worth saying plainly. The natural explanation for the Zakynthos formations is not a lesser story. It is a different story, and in some ways it is a stranger and more remarkable one. Consider what it actually describes. Several million years ago, in what is now the floor of the Ionian Sea, hydrocarbons were seeping upward through cracks in the rock. Methane, rising slowly through sediment that was perhaps a coastal zone or a shallow sea floor, was being consumed by microbial communities living in the sediment, communities that existed in near total darkness and derived their energy not from sunlight but from chemical reactions. As those microbes metabolized the methane, they altered the chemistry of the surrounding sediment in a way that caused dolomite to crystallize in place, molecule by molecule, over thousands or millions of years. The geometry of the fluid flow determined the geometry of the stone. Where fluids rose through a single conduit, a cylinder formed. Where they spread outward from a central point, a ring formed. Where they spread through a horizontal layer, a flat crust formed. The stone grew in the dark, in the cold, shaped by chemistry and fluid dynamics and time, with no intention behind it at all. And then, over further millions of years, the softer sediment around it eroded away, and the harder dolomite was left standing on the seafloor, looking for all the world like something a builder had set in place. That is a remarkable story. It involves deep time, invisible microbial life, the physics of fluid movement through porous rock, and the slow patient work of chemistry operating over geological timescales. It connects the Zakynthos seafloor to similar formations in the Gulf of Mexico and the Norwegian Sea and the Black Sea, reminding us that the Earth's seafloors are full of these slow chemical processes, building things in the dark that no one sees. It is a story about a planet that is far more active and far more creative, in a purely physical sense, than most people think about when they look at a stretch of ocean from a beach. The ocean floor is not a passive surface. It is a place where things are happening, slowly, constantly, invisibly, driven by the heat and pressure and chemical gradients of a geologically active world. The Lost City story, by contrast, is ultimately a human story, projected onto a natural surface. It is about us, about our desire to find evidence of civilizations more ancient and more accomplished than the ones we know, about the Atlantis-shaped space in our collective imagination, that is always ready to be filled by whatever looks like it might fit. That desire is not nothing. It is connected to something real in human experience, a sense that the past is larger than the record we have of it, that the world contains losses we cannot fully account for. That feeling is worth taking seriously, but it does not change what the formations at Zakynthos actually are. What is perhaps most interesting in the end is the question of what it takes for a scientific conclusion to actually reach people in a way that changes how they think about something. The Zakynthos paper is clear, the methodology is sound, the conclusion is well supported, and yet the lost city narrative persists in corners of the internet, and in travel writing, and in the minds of people who saw the original photographs and never saw the follow-up. The science did its job. The communication of the science is where the difficulty lies, and that difficulty is not unique to geology or to underwater formations. It is a general feature of how knowledge moves through a culture that produces far more information than any individual can process, and in which the emotional resonance of an idea is often a better predictor of how far it travels than its accuracy. This is not a reason for despair. It is a reason for patience, and for the continued unglamorous work of explaining things carefully to people who are genuinely curious, which is most people, most of the time, when they encounter something that surprises them. The snorkeler who photographed those formations in 2013 was curious. The journalists who wrote about them were, in their way, curious. The people who shared the photographs on social media were curious. Curiosity is the starting point. The question is what happens to it next, whether it gets fed more romance or more reality, and whether reality, when it arrives, is presented in a way that feels like a gift rather than a correction. What is actually happening at the seafloor off Zakynthos right now, underneath the surface of that clear shallow water, is something the geology can begin to tell us. The seafloor off Alicarnas is not a quiet place, even if it looks like one from above. Stand on the beach and look out at that shallow turquoise water, and what you see is calm. The surface moves gently, the light reflects back in long, broken patterns. It looks like the kind of water that has been the same for a very long time, but that impression is misleading because the geology underneath it is anything but still. The Ionian Sea sits over one of the most tectonically restless regions in Europe. The African plate is moving northward, slowly and steadily, grinding beneath the Eurasian plate along the Hellenic subduction zone, which runs in a long arc from the northwest down through the Ionian and into the eastern Mediterranean. Zakynthos sits almost directly above this boundary. The island has been shaped by it, lifted by it, and periodically shaken apart by it. The 1953 earthquake that struck the Ionian Islands, registering at magnitude 7.2, was powerful enough to destroy most of the buildings on Zakynthos and collapse entire towns. That was not an unusual event in geological terms for this region. It was simply the most recent large expression of forces that have been operating here for millions of years, and will continue operating long after any particular headline has faded. What this means for the sea floor is that the rock beneath it is fractured and stressed in ways that create pathways. Fluids move through those pathways. Hydrocarbons, water under pressure, gases including methane, all of these migrate upward through the crust, following the geometry of faults and cracks and permeable layers. This process has been documented across the broader Ionian region. Hydrocarbon seeps are not rare in the Mediterranean. They are part of the background activity of a basin that formed through rifting and subduction and has accumulated organic sediments over millions of years. The chemistry that built the Zakynthos formations was not a local anomaly. It was an expression of regional geology, a specific instance of something that happens across a very large area of sea floor. What makes the Alicarnas site particular is the depth and the visibility. The formations sit between roughly 2 and 5 meters of water. That is shallow enough for natural light to reach them clearly, shallow enough for a snorkeler with no special equipment to float directly above them and see them in detail. In deeper water, Structures like these would be known only to researchers with submersibles or sonar equipment. Here, they are accessible to anyone who puts on a mask and fins on a summer afternoon. That accessibility is part of why they became famous in 2013, and it is also part of why they remain a draw for visitors today. If you were to go there now, to actually enter the water at Alcanas Bay and swim out to where the formations lie, what you would find is something that takes a moment to read properly. The water is clear. The light comes through it in long shifting columns, the way shallow Mediterranean water tends to do, moving constantly as the surface ripples above. The seafloor in the surrounding area is sandy and relatively featureless, which is part of what makes the formation stand out so immediately. Against that pale sand, the dolomite structures are a different colour, a harder, denser pale grey, and they sit proud of the sediment in a way that makes them look placed rather than grown. The circular formations are the most striking thing. Some of them are large, a metre or more across, and they have a distinct ring shape, a raised outer edge with a slightly lower centre, which is exactly the geometry you would expect from fluid that spread outward from a central point and precipitated mineral along the outer edge of its flow. To a human eye, they look like the bases of columns, or like the stone rings used in ancient construction. The resemblance is not superficial. It is specific enough that even looking at photographs with the geological explanation in mind, you can still feel the pull of the architectural reading. The brain does not easily let go of it. The column-like structures are also present, though some of them are broken or lying on their sides, which adds to the ruin-like impression. Upright, they are roughly cylindrical, wider at the base, narrowing slightly toward the top, which again is exactly what you would expect from a conduit structure where fluid rose through a narrow crack and precipitated outward. The outer surface of the dolomite is irregular and rough in the way that natural mineral growth tends to be, not smoothed or dressed in the way quarried stone would be. But in the filtered light of shallow water, that roughness reads as weathering, as the kind of surface damage you would expect from stone that has been submerged for centuries. The flat, paved-looking surfaces are perhaps the most convincing element of the whole site. There are areas where the seafloor appears to be covered in a continuous hard crust of dolomite, broken into irregular but roughly rectangular sections by natural fracturing. In photographs, this looks almost exactly like a stone-paved courtyard that has been broken apart by time. The sections are not perfectly regular, but they are regular enough, and the way they sit flush with each other, separated by thin gaps, looks deliberate. The geological explanation for this is straightforward. Fluids spread laterally through a horizontal sediment layer, the dolomite crystallized through that layer uniformly, and then fracturing along natural stress lines broke the crust into sections. But knowing that does not entirely dissolve the visual impression. What is different now compared to 2013 is the biology. Hard substrate on a sandy seafloor is a resource, and organisms that need something solid to attach to will find it and colonize it. The dolomite formations at Alcanas are no longer bare stone. They are increasingly covered with marine life. Encrusting algae have taken hold on many surfaces, giving the stone a darker, softer appearance in places. Sea urchins, the long-spined black variety common in the Mediterranean, have settled into the crevices and depressions, where they graze on algae and contribute to the slow biological erosion of the surface. Small fish use the formations as shelter, darting between the column shapes and resting in the shadows of the larger ring structures. Sponges have begun to establish themselves in spots where the current brings enough nutrients. This biological colonization is doing something interesting to the appearance of the site. In some ways, it makes the formations look more like ruins, because archaeological sites in the Mediterranean are typically encrusted with marine life after centuries of submersion, and the visual texture of a dolomite column covered in algae and urchins is not entirely different from that of a marble column in the same condition, but it is also slowly softening the hard geometric edges of the structures, filling in the gaps and covering the surfaces in a way that will, over long enough time, change how the formations look entirely. The sea does not preserve things, it transforms them. The tectonic activity continues in the background. Zakynthos experiences earthquakes regularly, most of them small, some of them not. Each significant seismic event reshapes the seafloor to some degree, shifting sediment, opening or closing small cracks, occasionally toppling structures that were already compromised. The 2018 earthquake that struck the island, a magnitude 6.4 event centred not far offshore, was a reminder that the forces which built these formations are still operating. The subduction zone does not rest. The fluids are still moving through the rock below, following pathways that have been open for millions of years. Whether there are active hydrocarbon seeps at the Archaeologists site right now in the present is something that would require direct measurement to confirm. The broader Ionian region has documented active seeps, and the geological conditions that produce the formations suggest that the plumbing system responsible for them has not necessarily shut down. It is possible that methane is still migrating upward through the seafloor in this area, though at what rate and through what specific pathways is not something that has been publicly documented for this particular site. The 2016 study focused on the mineralogy and geochemistry of the existing formations rather than on monitoring for ongoing seep activity. That would be a different kind of study, requiring different equipment, and it has not, as far as the published record shows, been carried out here. What has been established is the broader geological context. The Ionian seafloor in this region is not a passive surface. It is part of a system that involves deep crustal processes, fluid migration, and the ongoing deformation of rock under tectonic stress. The formations at Archaeologists are a record of that system operating at a particular time and in a particular way, millions of years ago, but the system itself is still running. The formations are, in a sense, geological artifacts of a process that has not ended. They are old, but the forces that made them are not. There is something quietly remarkable about that framing. When people talk about the Zakynthos site as a lost city, the implied timeline is human scale, a few thousand years, the kind of time that separates us from ancient Greece or from the Bronze Age. But the actual timeline of these formations is orders of magnitude longer, 2 to 5 million years. The dolomite was crystallizing here when the Mediterranean was a different sea, when the climate was different, when the species living on this planet were different. Hominids existed, but Homo sapiens did not. The stone that a snorkeler in 2013 mistook for ancient human construction is older than our species by a very wide margin. That is a different kind of age than the one the Lost City story implies, and it is worth sitting with for a moment. The formations are not old in the way that ruins are old, carrying the weight of human time and human loss. They are old in the way that mountains are old, or the way ocean basins are old, shaped by processes that operate on timescales so long they are genuinely difficult to hold in the mind. And yet they sit in 2 to 5 meters of water, in clear Mediterranean light, accessible to anyone willing to swim out from a beach. There is something almost absurd about that proximity, about the fact that you can float above a geological structure that is millions of years old and see it clearly with the naked eye on a sunny afternoon. The site has no formal protected status as an archaeological site, because it is not an archaeological site. The Greek Ministry of Culture's investigation confirmed this, and the 2016 scientific study confirmed it again from a different direction. There is no legal framework for protecting a geological formation of this kind, in the same way that a Bronze Age site would be protected. Visitors can swim there. Divers can approach the formations closely. There is no prohibition on touching them, though responsible diving practice would suggest not disturbing the marine life that has colonised the surfaces. This lack of formal protection is, in a practical sense, fine, because the formations are dolomite, and they are not fragile in the way that archaeological artefacts are fragile. They are not going to be damaged by a snorkeler running a hand along a surface. What could damage them over longer timescales is the same thing that damages all seafloor geology. Major seismic events, changes in sediment dynamics, and the slow biological and chemical weathering that operates on any exposed rock surface in the sea but those processes operate on timescales that make human visitor impact essentially irrelevant. What the site does attract, practically speaking, is tourism. Zakynthos is already a popular destination, known for the Navigio shipwreck beach, for the loggerhead sea turtle nesting sites at Lagana's Bay, for the blue caves on the northern coast. The underwater formations at Alikanas have become another item on that list, another reason to get into the water. Tour operators offer snorkeling excursions to the site. Travel blogs and diving websites describe it, often still using language that hedges between the geological explanation and the Lost City framing, because the Lost City framing is simply more compelling to write about and more likely to attract readers. The formations draw people who are curious about what they have seen in photographs, and those people generally find the site impressive in person, regardless of what they believe about its origin. There is a version of this story in which the scientific explanation and the tourism draw are in tension, where the myth brings visitors and the science risks deflating the experience. But that tension is probably overstated. The formations are visually striking whether you know they are natural or not. A diver floating above a large circular dolomite structure in clear water, watching light move across it, while a sea urchin navigates slowly along the rim, is having a genuine experience of something real and interesting. The explanation for what they are looking at does not diminish that experience. It deepens it, if anything, because understanding what you are looking at is almost always more satisfying than simply being impressed by it. The seafloor continues to change, slowly and mostly invisibly, in the way that geology always does. The soft sediment around the formations shifts with currents and storms. The biological community on the hard substrate develops year by year. The tectonic forces beneath the Ionian continue their work, building stress in the crust that will eventually release in earthquakes, some small and some not. The dolomite itself is stable on human timescales, resistant to the kind of chemical weathering that would affect it significantly over centuries. But on geological timescales, it is temporary, like everything else. What the site at Alikanas represents, in the end, is a kind of window, not into human history, which is what people initially hoped for, but into geological process. The formations are a record of how the Earth's interior communicates with its surface, how fluids moving through rock carry chemistry upward and deposit it in forms that reflect the geometry of their movement. They are a record of deep time made visible in shallow water, which is a genuinely unusual thing to be able to encounter without specialised equipment. Most of the geological record is buried or inaccessible. This one is not. It is sitting in 2 to 5 metres of clear water off a beach that anyone can visit. And that visibility, that accessibility, is ultimately what connects the geology to the question of perception that the site raises so clearly. The formations look the way they look because of specific physical processes. The human response to how they look says something specific about how human perception works. Both of those things are interesting. Both of them are worth understanding. And the relationship between them, between the world's capacity to produce shapes that resemble human work and the human mind's readiness to read intention into those shapes, is something the Zakynthos site illustrates better than almost any other example in recent memory. What that relationship tells us more broadly about how we read the natural world is a question the site keeps asking, quietly, from the floor of the Ionian Sea. So let us go back to the beginning of this particular story. Back to 2013, to a beach at Alikanas on the northern coast of Zakynthos, to a snorkeler floating in shallow water on what was probably an ordinary afternoon. The light in the Ionian in summer has a particular quality, clear and warm, the kind of light that makes the seafloor visible from the surface in a way that feels almost too good to be true. And there, beneath a few meters of that clear water, something appeared that looked exactly like what human hands leave behind. Paved surfaces, cylindrical columns, circular formations arranged with what seemed like deliberate geometry. The feeling that person must have had floating there, looking down, is not hard to imagine. The sense of having stumbled onto something hidden, something waiting. The particular mixture of disbelief and excitement that comes when the world seems to be offering you a secret. That feeling was real. Whatever was happening in the mind of that snorkeler, it was a genuine response to a genuine thing. The formations are there. They are visible. They are impressive. The feeling of discovery was not manufactured or mistaken in any simple sense. What was mistaken was the interpretation, and that is a very different thing. The feeling of wonder was entirely appropriate. It was just pointed at the wrong explanation. That distinction matters, because it is easy to tell this story as a story about being wrong, about the gap between what people thought they found and what was actually there. And that framing is not inaccurate exactly, but it misses something. The snorkeler was not foolish for thinking what they thought. The journalists who wrote about lost cities were not simply being irresponsible. The people who looked at photographs online and felt certain they were seeing ancient ruins were responding to real visual information in a way that made sense given what human brains are built to do. The error was not a failure of intelligence. It was a demonstration of how perception works, of how powerfully the mind reaches for familiar patterns when it encounters something ambiguous. And the natural world, it turns out, is full of ambiguity of exactly this kind. The planet has been building things for 4.5 billion years without any concern for whether they look intentional or not. Some of those things happen to look like columns, some happen to look like paving stones, some happen to look like walls, or roads, or the kind of careful geometric arrangements that human civilizations leave behind. That is not a coincidence in some cosmic sense. It is just what happens when physical processes repeat themselves across space and time, when the same chemistry plays out through the same geometry over and over until the results start to resemble each other in ways that catch the eye. The process that built the Zakynthos formations is, in its own right, a remarkable thing to think about. Methane and other hydrocarbon-rich fluids moving upward through the rock of the seafloor, following cracks and pores in the sediment, carrying dissolved minerals with them. As those fluids reach zones where the chemistry changes, where they encounter seawater or different sediment, the minerals they carry begin to precipitate out. They crystallize, they harden, and they do this in the shape of the space they are moving through, which is why a fluid rising through a narrow vertical conduit leaves behind a cylinder, and why a fluid spreading outward from a central point leaves behind a ring. The geometry of the stone is the geometry of the fluid's movement, preserved in mineral form. It is a record in a very literal sense. A record not of human intention but of physical process, written in dolomite and readable, if you know the language, millions of years later. Those formations sat in place as the world changed around them. The sea level shifted, sediment accumulated and then eroded. The softer material around the dolomite wore away, leaving the harder structures standing proud of the seafloor in a way that made them look even more like ruins, because ruins are also hard things left standing after softer things have gone. The resemblance is structural, not accidental. Both ruins and these formations are the product of differential erosion, of harder material surviving while softer material disappears. The planet and human civilization arrived at similar-looking results through completely different routes. There is something in that fact that feels worth sitting with for a moment. The Earth did not need human builders to produce something that looks like a built environment. It had its own processes, its own chemistry, its own geometry, operating across timescales that make human history look brief, and yet the output, the visual result, is something that a human eye reads immediately as familiar. That says something about geology. It also says something about us, about the depth of the pattern recognition that runs through human perception, about how thoroughly the experience of living in built environments has shaped what we see when we look at the world. The scientific investigation that followed the 2013 discovery did not set out to be a corrective. It set out to answer a question. The researchers who collected samples, who prepared thin sections for microscopy, who ran isotope analyses and compared the results to known databases of methane-derived carbonate formations, were not trying to deflate a myth. They were trying to understand what they were looking at. and what they found was genuinely interesting, not as a consolation prize for the absence of archaeology, but as a result in its own right. The isotope signatures, the crystal fabric, the specific mineralogy of the dolomite, the complete absence of any cultural material in the matrix, all of it pointed toward a coherent and well-documented natural process. The 2016 paper in Marine and Petroleum Geology was not a paper about what was not there. It was a paper about what was. That is what good science does, really. It replaces one question with a more specific answer, and the answer opens up into its own set of further questions. What was the fluid composition at the time of formation? How long did the seepage last? Are there similar formations elsewhere in the Ionian that have not yet been found? What does the distribution of these structures tell us about the subsurface geology of the region? The Lost City framing closed the question down into something simple and romantic. The geological explanation opened it back up into something genuinely complex and ongoing. And the Ionian Sea is ongoing. That is something easy to forget when looking at photographs of stone formations on a seafloor. The region is not a museum. The Hellenic subduction zone is still active. Zakynthos still experiences earthquakes with a regularity that residents are accustomed to, but that visitors often find startling. The African plate is still moving beneath the Eurasian plate, still driving the same tectonic forces that created the fluid migration pathways that built the dolomite structures in the first place. The seafloor near Alicanus is not the same seafloor it was 1,000 years ago, and it will not be the same seafloor 1,000 years from now. The formations themselves are stable on human timescales, but the world around them is not. There is a particular kind of humility that comes from understanding geological time, from really trying to hold in the mind what it means that these structures formed during the Pliocene epoch, 2 to 5 million years ago, when the ancestors of modern humans had not yet appeared on the planet. The formations were already old, already eroded to something close to their current shape. Long before anyone was around to look at them, they did not wait to be discovered. They were simply there, in the dark water, doing what stone does, which is essentially nothing, for a very long time. And then, one afternoon in 2013, a person with a snorkel floated above them, and the story changed. Not the geological story, which continued exactly as it had been continuing, but the human story, which is the kind of story that starts the moment someone notices something and decides it matters. The photographs went out. The headlines appeared. The word Atlantis was used, as it always is, because Atlantis is the word that gets used whenever anything old and submerged is found anywhere near the Mediterranean. Plato wrote his account of Atlantis around 360 BCE, and in the 2,500 years since then, the myth has proven essentially indestructible. Every generation finds a new candidate. Every underwater discovery near Greece or the Canary Islands or the Azores gets held up briefly against the template. And then the investigation happens, and the specific details do not match, and the candidate is quietly set aside, and the search continues, because the search for Atlantis is not really about Atlantis. It is about the desire for a lost world, for the idea that something vast and sophisticated existed before our records began and was taken by the sea. That desire is not going away. It is too deep, too old, too tied to something fundamental in how humans relate to time and loss. The Zakynthos formations will keep attracting visitors who have heard the Lost City version of the story. Some of those visitors will read the scientific explanation and find it satisfying. Some will remain attached to the idea that something was missed, that the official conclusion was too quick, that the formations are too regular to be natural. That is a predictable human response, and it is not entirely without value. Skepticism toward official explanations is sometimes warranted. The history of archaeology and geology includes cases where the consensus was wrong, where a site was dismissed and later found to be significant. Healthy skepticism is part of how knowledge advances, but skepticism has to be calibrated to evidence. At Zakynthos, the evidence is not thin or ambiguous. The The petrographic analysis is specific. The isotope chemistry is specific. The comparison to documented seep carbonate formations in other parts of the world is specific. The complete absence of any artifact, any tool mark, any construction joint, any pottery, any coin, any organic material associated with habitation, that absence is itself a form of evidence, and it is a loud one. The formations were examined by people whose professional expertise is exactly this kind of question, and they reached a clear conclusion using methods that are well established and reproducible. The conclusion is not a matter of opinion. What is a matter of interpretation, though, is what the story means, and that is where it gets more interesting than the simple question of natural versus man-made. The Zakynthos story is a story about perception, about how the human visual system interacts with the physical world in ways that are not always accurate but are always meaningful. The snorkeler who saw ruins was not seeing nothing. They were seeing real shapes and processing them through a real cognitive system that is tuned, by evolution and by experience, to find patterns and assign them to familiar categories. That system works extraordinarily well most of the time. It is the same system that lets you recognise a face in a crowd, or read handwriting, or navigate a city. It is just not perfectly calibrated for distinguishing natural dolomite formations from ancient architecture, because that is not a distinction that came up often enough in human evolutionary history to require a dedicated cognitive module. The planet is older and stranger than the pattern recognition system expects. It has had more time to produce more variety than any human framework is really prepared for, and occasionally it produces something that falls directly into the overlap between what geology makes and what civilization makes, and that overlap is where stories like this one live. The formations at Alicanas are still there. They will be there tomorrow and next year and a century from now, more or less as they are, give or take the slow biological colonization of their surfaces and the occasional shuffling of sediment by currents and storms. The sea urchins will continue their patient navigation of the dolomite rims. The small fish will continue using the circular formations as shelter. The light will continue to fall through the shallow water in that particular Mediterranean way that makes everything on the seafloor look slightly more significant than it might otherwise. Visitors will continue to swim out from the beach at Alicanas and float above the formations and feel something, whatever it is they feel, looking down at shapes that the Earth made over millions of years and that look, from a few meters above, like the work of human hands. That feeling is not a mistake. It is an invitation to ask what you are actually looking at, to follow the question past the first impression and into the specific, patient, genuinely fascinating answer that the science provides. The answer is not less wonderful than the myth. It is differently wonderful, more slowly wonderful, the kind of wonder that builds as you understand more rather than collapsing the moment you look closely. A lost city would have been remarkable for what it told us about human history. The actual explanation is remarkable for what it tells us about geological time, about fluid dynamics, about the chemistry of the deep earth, and about the strange, beautiful fact that the planet can build things that look, to human eyes, like civilization. The Ionian Sea keeps its own time. It was here long before the first Greek sailors crossed it, and it will be here long after the last photograph of the Zakynthos formations has been uploaded to the last travel blog. The dolomite does not know it was mistaken for ruins. The methane that seeped through ancient sediment and left these shapes behind was not trying to make anything. It was just chemistry, moving through rock, following the path of least resistance, crystallizing where conditions allowed, leaving behind a record that would take millions of years to become visible, and a few months to be misread and a few years to be properly understood. That sequence, the long formation, the brief misreading, the careful correction, is itself a kind of story about how knowledge works, about the gap between first impressions and careful investigation, about the value of going back, of looking again, of asking what the evidence actually says rather than what the initial impression suggested. The snorkeler in 2013 looked down and saw a lost city. The researchers in 2016 looked at the same formations through a microscope and saw something older and stranger. Both of them were paying attention. Only one of them was right. And being right in this case meant being willing to let the more interesting explanation win, even if it was harder to put in a headline. Thank you for spending this time here tonight. If you have been listening from somewhere near the water, or somewhere far from it, I hope this gave you something quiet and interesting to think about. If you found the story worthwhile, a like or a subscription genuinely helps this channel continue, and it is always appreciated more than you might think. And if you have thoughts about the Zakynthos formations, about natural formations that look man-made, about the Yonaguni debate, or about anything else this story brought to mind, the comments are a good place for that. I read them. Take care of yourselves, and good night.